static analysis, program analysis, really. This is a general session. We have 5 talks, and the first talk is going to be given by Evan Chang, one of the pillars of the community. Please.
Thank you, Jens. So this is really work. It's part of the PhD work of my student Benno Stein, and he couldn't be here, so I get the opportunity to talk to you today. Okay, so all right, so here's the context. Today, when a developer submits a code review, then often it's commented by their team members, but now also increasingly it's commented by a bot, right? That is backed by a static analyzer. And what we want to do is make the static analyzers do a bunch of thorough reasoning to flag semantically deep issues to help us build better software, right? So let's suppose we're in this great situation where this analyzer flags some deep and real and important issue. Then, well, now the developer, when they wakes up, they want to kind of fix that, right, and submit a bunch of changes. And if they do this now today, then it's going to take a while, right? And this is going to be a kind of frustrating experience because, well, really, maybe it's just a one-line change that they have to do, or they just care about the error that was flagged at line 8, right? So the need here is to make analysis interactive, right? To make it incremental on these edits, on these subsequent edits, and demand-driven on queries, this particular query on line 8, right? So this is the task that we set out to do, that the analyze user needs this to be interactive as they make edits and issue queries, but also that we want it to be consistent with the underlying batch analyzer that ran overnight. And then now also what we're thinking is that the analysis designer doesn't really want to implement 2 versions, right? This really needs to be push button, and they don't need to sort of ad hoc think about criminalization. And it needs to be general with respect to whatever abstract domains they already implemented for their batch analyzer. So let me unpack what a static analyzer looks like today often. So behind that magic that takes a program and produces an over-approximate set of facts, there's usually 2 parts. One part is what's called the abstract domain, which assigns the set of abstract states or facts that you care about the program, and then operations over it like transfer functions, join, wide, and so forth, right? And then a separate part that is like a very generic abstract interpretation engine. So for example, using the standard work list-based fixed point algorithm. Now, this picture that I'm drawing here is intentionally very, very classical. Right? And why? Because it's very general and a well-studied soundness theory. Right? So in fact, the focus here is on general. We want to support whatever infinite height abstract domains you care about. It doesn't need to have a best abstraction. However, you need to do to reason about your program. Right? So now if we look at an interactive abstract interpretation framework that we're trying to build, what we're trying to do is really just drop that standard engine and replace it one that is a demanded abstract interpretation engine that supports demand-driven queries. What is the abstract state at this program location? Incremental reevaluation on edits to add, edit, or delete statements, and then have strong consistency results, what we call from-scratch consistency, right? That query responses are guaranteed to be the same as the batch analysis on the current program version. And in particular, this domain interface should remain unchanged. In my animation, nothing changed, right? Okay. All right. Okay. So, we did this a little bit, right, in some prior work on reifying an abstract interpretation computation, right? Essentially taking that computation and putting it into a structure that we call a demanded abstract interpretation graph, or a DAG, that reifies the dependency structure of that abstract interpretation computation. And what that's composed of is reference cell vertices that cache program syntax and abstract states in order to be incremental, and that could be potentially empty to support demand. And then these vertices were connected by computation edges that acyclically connect those and are labeled by these domain functions like the transfer functions, join and widen. Right? So let me draw a little picture of that. Right? So here, the gear here kind of represents the abstract interpreter crawling over a control flow graph here with just a single statement S. Right? And that reification, sort of the corresponding DAG snippet, looks something like this. Right? We have boxes to represent cells here that cache states. And then between those cells are analysis computation labels. Right? And so this is that reification of the abstract interpretation I'm talking about, waiting to be demanded. Right? So that is, if we care about, like, oh, we want to ask what is the abstract state at L prime, we want to demand there, then demand might need to go recursively backwards to compute the state at L. But once it has that, then it just supplies the analysis computation label and gets us 5 prime here. Okay. right? Now if we have some edit here, that statement changes from S to S prime, then we just dirty and mark everything forward, right, for later incremental reevaluation if it's demanded again. Okay. Very simple picture, right? This all makes sense if it's acyclic like in this picture, right? But cyclic dependencies will make query evaluation undefined, and so that's kind of the tricky part here. Okay, so if we pop back up to where we are today, right, this picture, right, this is what we want to support, right? Then that all works from this prior work if, we just have a single control flow graph, if we just have main, right? But of course, real programs have procedures, right? Main calls foo calls bar, right? And so then what is that sort of corresponding engine here, right? And that's what we're going to talk about today. That supports demand-driven queries, incremental reevaluations, now with procedures, but also importantly, we want to guarantee from scratch consistent results. Okay? All right, and of course, the hard part here is like, well, what if bar is recursive and programs, that have recursion, have loops, so how do we do that? And that's what we call demanded summarization. All right, so contributions of this particular paper are about really this demanded summarization. So we introduced the idea of a demanded summarization graph that reifies the dependency structure of a summary-based abstract interpretation computation. A DSG turns cyclic dependencies, or sort of what would naturally be cyclic dependencies from recursion, into acyclic DAGs with self-referential demanded summaries, and I'll say what that is. And then we have a formalization where we are, careful formalization to prove that demanded summarization is terminating and from scratch consistent, okay, and therefore sound. Right? If it's consistent with the batch analyzer sound, then from scratch consistent demanded analyzer would be sound. Okay, so let me sketch the kind of idea here of a demanded summarization graph. Or I guess first I'm going to kind of put out the naive approach, right? Is that we could build one big interprocedural DAG, right? Combine all the control flow graphs into one, conceptually, interprocedural flow graph, and then build a single interprocedural DAG structure, right? So take the CFGs from those procedures, their corresponding DAGs, wire them together with call return edges, right? Now, of course, if we just directly do that with recursion, we're going to break that acyclicity invariant. And also, it just doesn't feel quite right, because it really doesn't leverage procedural abstraction, because in this structure, if we edit like at the beginning of the program, then everything through the entire program becomes dirty. Right? So we don't have, right. So it kind of feels overly conservative. Okay, so in our approach of a demanded summarization graph, okay, so a DSG reifies the dependency structure of a summary-based abstract interpretation computation. Okay, so what are those pieces? Now our vertices are going to be DAGs themselves that compute procedure summaries on demand. Right? So if I have main, foo, and bar, then now the corresponding DAGs can correspond to procedure summaries. Right? Or really, the DSG doesn't really care what's underneath. You could have some other way to compute procedure summaries, but for concreteness, I'm going to instantiate them with DAGs. Now, then what a DSG sort of represents is summarization edges that connect the return cells, the DAGs that need to use procedure summaries with the procedure summaries that we demand, right? So then the overall structure is a DSG of demanded DAGs. Okay. Right. Now if we have recursion in our, in bar, in our program, right, then we record, some sort of self-referential summary applications as interprocedural dependencies, but because of this hierarchy of DSG and DAGs underneath, then we kind of maintain the acyclicity invariant. Okay, so let me illustrate that. Okay, so DSGs record the use of a procedure summary. So here, this is our running example where main calls foo. Right? So if we were trying to get the state at L prime, the DAG evaluation gets stuck at L prime, depends on a summary of foo. So at that point, we might construct or maybe reuse something that already exists, a DAG for the call E, initializing that entry location at L. And then we'll just demand the, and query at the exit to get phi prime at the exit. And then this fully solved DAG is effectively a Hoare-style procedure summary, very classical, and we're used to, that we can just apply back and, say, well, the state at L prime is phi prime. But importantly, when we do that application, we record that dependency, right? So this DSG edge that we introduce in purple here is that L prime in main depends on the summary of foo with this procedure entry state phi, right? And then we would dirty L prime if this particular summary is ever dirtied. Now we do leverage procedural abstraction. It's compositional, and that edits in the callers will never affect any of these further demanded summaries. Right? There is no sort of edge from at the call site, for example. Okay, so let me say a little bit about the complexities of recursion. So with self-referential demanded summaries, right? So yes, there's going to, recursion means there's going to be a fixed point iteration. That should not be a surprise, right? But the hierarchy between the DSG and DAGs prevents, this sort of dreaded cyclic dependencies. Okay, so in our example, bar is recursive. Bar calls itself. So embedded in the bar DAG, there's a call to itself. Right? So maybe we can demand up to the call site and get phi call. Now, if we're trying to get L prime, we'll discover that we want to reuse this same summary that we're in the middle of computing, right? Because phi call is included in phi. And this is what we call a self-referential summary query. Now, doing kind of essentially the same thing as before, right, is that we want to query at its exit state, but we want to specifically say query for its exit state at fixed point. And that might need to use this interprocedural DAG dirtying, to do this iteration. But, after that's done, then really it's kind of the same, right? There's now a dependency at the return site to itself, it happens to be, but it really is the same picture, right? A DSG edge, L prime and bar depends on the self-referential summary of bar with a procedure entry state phi. Okay? But importantly, each of the underlying DAGs remains acyclic, and so the dirtying and querying algorithm kind of remain okay. All right, let's see time. All right, okay, so that's the taste, right? So let me give a taste of the formalization, right? So interactive summary-based abstract interpretation is realized through two parts, right? One part is this demand-driven query evaluation that creates a summary use dependencies that says, in a DSG, a query at L under entry state phi, yields a state L phi prime at L, and an updated DSG, right? And we kind of talked that there's, that depends on two bits that might generate summary edges, right? That if we're stuck at N, then we need to get a procedure summary that adds a summary dependency edge. Or if we're in some recursive situation and we demand a self-referential summary, then we have some recursive summary dependency. But once we have that, then, we're in a situation where in DSG that we have a subsequent edit, right? That, an edit of cell N, with statement S, just results in yields a dirty DSG, and we can sort of continue this process, right? But the summary here is that, demanded summary use dependencies that we create through this query evaluation that we carefully created enables this proof of from scratch consistency. Okay. All right. Okay, so does this work? Let me show you a little bit about that, right? So in fact, our goal of being interactive, does demanded summarization enable responsive queries after edits? Okay. So what we did was generate random program edits with looped procedures, conditionals, using a probabilistic grammar, right? And comparing an analysis, in this case, trying to use a precise or a deep analysis using octagons, right? And compare the latency for 4 configurations, 3 baselines or batch incremental demand driven, and then demanded, which is the combination of the two, incremental demand driven, on a sequence of 2,500 edits. Okay? So that's the setup. Let me show you kind of one way of looking at this data. So here's a cumulative distribution graph where the y-axis is the fraction that are completed within the sort of analysis latency on the x-axis. Okay? So that is, if I draw this sort of 95th percentile line, or P95, then wherever it crosses the point is the 95th percentile will complete within that n-second latency. Okay. So taking that data, I can sort of summarize it into a table on the right, where of these, again, these 4 configurations, right? So the mean and P50 show that there's already some separation demanded. It starts to separate it more at the P95 level. And that P99 at the 99th percentile slowest run, right? Then the separation really becomes quite evident. So this provides some evidence for mitigating the sort of worst case analysis cost, right? We don't, we want really in the tail that we want to sort of enable for interactivity. All right, so how about in practice? how much does demanded summarization reduce reanalysis in practice? Okay. So for this, there's this very nice data set out there on the bug swarm data set of real Java bug fix pairs mined from GitHub. So that means we can get a particular commit with an edit. So here are those benchmarks and the lines of code of those benchmarks. And then the second column are the number of lines that are edited in that particular commit. Okay. So then we consider running analysis with 3 different abstract domains: intervals, octagons, and nulls. I'm only showing the summaries for the octagons and nulls because of space, but they're there, right, in the paper. And then now, on the initial version, we run the batch analysis. So that's, imagine the overnight run, right? That's the number of states that get computed by that sort of batch analysis. And then in the 3 subsequent configurations I'm showing the percentage of the batch states that need to be recomputed on the edit, right? In the sort of incremental but not demand-driven, the demand-driven but not incremental, and the demanded version. And really, I guess the take-home message is that we're really only recomputing a very small number of the overall number of states that the batch analysis does, either from 0.1 to 2.7%. Right? Okay. All right, so timing right on. So in conclusion, a demanded summarization graph reifies the dependency structure of a summary-based abstract interpretation computation. A DSG turns cyclic dependencies from recursion into acyclic DAGs with sufferential demanded summaries. And we've done a careful formalization where we've proven demanded summarization terminating and from scratch consistent, and therefore sound. So with that, I show you a beautiful picture of Boulder for you to come visit. And then otherwise, I'm happy to take your questions.
Thank you. We have a microphone. Come up, come up.
Thanks for the great talk. I'm curious how widening fits into this framework.
Yeah, so the widening becomes part of the engine. And so whatever widening is supported in terms of your infinite height domains. And just like I showed in recursion, the widening gets used in that sort of fixed point computation, the sort of usual thing, unless you had a more specific question missing.
I guess there's the issue of one could the widening heuristics, like when to apply widening, might not be stable because those exist outside of the fixed point definition.
Yeah, so I mean, it does say that our engine kind of fixes a particular widening strategy, or you sort of count on the widening strategies that our engine would provide, right? And of course, that would be a great thing to think about how to make that under the control of the analysis designer versus the framework. But so yeah, exactly. That becomes great, excellent future work.
Thank you for an interesting talk. My question is regarding the recursion. Does your approach handle indirect recursion via multiple functions? Or is there anything that has to be added or extended in that situation, if there is a cycle intercall graph involving more than one method?
Yes, okay, so the tricky part, of course, is detecting when you need to switch gears from the normal sort of summary dependency introduction and when you need to introduce a self-referential summary. So if you wanted to sort of, if you will, pre-compute the sort of like a strongly connected component and say, oh, whenever you're in that, then it's a self-referential summary, then you could do that. For the simplicity of our formalization, we just do it where we assume you only have sort of single recursion. Or you can think about it as like, oh, you translated all mutual recursion into like, one method that dispatches between them recursively, something like that, right?
Thank you.
Yeah, good question.
Following up on that question, imagine a kind of a worst case program. You have an entry point that calls a method, that calls all of the other stuff in the program, then returns to the first method. In that case, wouldn't kind of much of the performance be lost because you would then have a self-recursive call that kind of includes your entire program? I mean, wouldn't it then make sense to have a mechanism to say, hey, I know that the stuff in the middle is kind of totally unchanged, and we can somehow pull it out of that loop?
So you're saying if you have an edit at the top and you sort of like, would that sort of dirty everything or something?
Yes, yes.
So exactly, that's kind of the nice bit of our approach is that it doesn't. Because there's no dirtying of the subsequent summaries if it's just an edit that's sort of the beginning of the program because there's no sort of call dependency.
Okay, I was just wondering, because then, following up to the previous question, you don't have this self-recursive or self-referencing summary from one function to itself, but to kind of a much higher point on the call stack.
So the question, well, it just depends on how, like, the summaries that make sense in the intermediary would be fine and unchanged, right?
Right, and can you detect this then?
I mean, I guess I can't say that we've, empirically tried it, but
Okay.
it seems like this would be possible. So, I mean, it's kind of in the details that we would have to sort of think about.
Thank you.
Yeah.
Very good. Let's thank the speaker again.
Yeah, thank you.
Okay, the next talk is by Mafalda Ferreira. And please.
Okay. Actually, this is missing here. I'm sorry. Yeah, but I'm not seeing the slides here. It worked when I tried it. I don't know where that is. Oh.
I give you the screen option. Running, I think so. Okay. And say that you need to
Yep, I just tried it earlier and it was.
to duplicate.
And it was. Okay, no, because I want to see like the presentation view.
I think that it should be yes.
Maybe.
Okay.
Okay, right. Okay, so hi everyone, I'm Mafalda Ferreira. I'm from the University of Lisbon in Portugal, and today I'm going to talk a bit about our work on efficient static vulnerability analysis for JavaScript using multi-version dependency graphs. So Node.js is a runtime environment that runs JavaScript on the server side. It is part of popular full-stack frameworks such as MERN and Min, and it has also been adopted by many high-profile companies such as Netflix and PayPal. In fact, according to the 2023 Stack Overflow Developer Survey, it is the most used web technology by developers. Node.js applications rely on a high number of third-party packages, which are mainly developed and shared by other developers. This package ecosystem, the Node Package Manager, NPM for short, currently offers more than 2.5 million packages for developers. However, as there's no prior verification before developers can publish these packages, these packages are often vulnerable. So let's look at an example of a critical vulnerability in a Node.js application, specifically a command injection. So here we have a git reset function, which is designed to revert a Git repository to a previous commit. And this function is exported by the package, and so its parameters can be controlled by an attacker from the outside. And we call these sources. In line 7, we have a call to the exec function, and this function will launch a shell process that will execute the given command, and we call this async. In this application, this call depends on the values of options command and options commit, which are properties of the options object. And this object is defined here in line 4 as a sub-object of the config object. And so we can see that by using a malicious config, an attacker is able to manipulate the value that will reach the sink and execute an arbitrary command. For instance, if an attacker uses the following configuration, it will be able to delete all files in the server. So to have secure Node.js applications, it is crucial that we have tools that help us detect these types of vulnerabilities. In our work, we focus on these 4 vulnerabilities: prototype pollution, command injection, code execution, and path reversal. So to help uncover these vulnerabilities, static analysis tools based on code property graphs have become increasingly popular over the last years. And this approach divides the analysis in 2 stages. So first we have the graph construction stage, in which it will build a graph representation of the given package, which we name the code property graph. And this code property graph includes 3 different types of program representations, namely the abstract syntax tree, the control flow graph, and the program dependence graph. Then, in a second stage, the tool will query the graph in search for patterns that may indicate potential vulnerabilities. For example, command injection or prototype pollution. The main advantage of these tools is that the search patterns are entirely customizable through the graph traversal in the second stage, and so this offers high flexibility in detecting different types of vulnerabilities. Even with the advances in CPGs, a fundamental challenge that remains is deciding how much information should we add to them so that the definition and the identification of these patterns is straightforward and precise. On the one hand, with more information, we have richer graphs, which allow for more precise vulnerability patterns. But the queries, this makes the queries very complex to specify and later identify, and it also worsens the performance. On the other hand, if we have less information, we have simpler graphs, which will improve the performance, but will limit the expressiveness of the patterns that we can search for. And so a fundamental challenge in using CPGs is actually figuring out where's the sweet spot of the information that we should add. Currently, ODGen, which is the state-of-the-art tool for vulnerability detection in Node.js packages, extends this concept of code property graphs with what they call the object dependence graph to model JavaScript objects. And although very precise, ODGen actually suffers from performance problems. In fact, ODGen is not able to finish the analysis in many cases, which causes it to miss vulnerabilities. So in this work, we set ourselves to improve this performance without losing precision. And how do we achieve this? So basically, we do this by, instead of including all of those program representations that ODGen includes, we rely on a single graph that models the evolution of the objects and their properties during program execution. And we call them multi-version dependency graphs. We also implemented GraphJS, which is a vulnerability scanner for NPM packages based on these MDGs. And our evaluation shows that we are able to analyze 37% more packages than ODGen and actually detect 63% more vulnerabilities without losing precision. So in sum, our graphs are smaller because they rely on a single and simplified structure. And because of this, they allow for simpler queries because they only need to iterate through a single structure without going back and forth all of those program representations, looking for syntax and flow information. The construction algorithm is also formalized and proven sound. So our multi-version dependency graphs encompass two existing analysis techniques. So they have shape analysis, where the objects are mapped to the properties that they have during program execution. So here, B represents property P of object A. And also dependency analysis, where the objects and values are mapped to the values that they depend on. So here, C depends on the values of A and B. And our novelty is that in the same graph, we also keep track of the data flows and execution order using version information. Specifically, we create new versions of objects anytime the object or its properties are updated. For instance, here, A1 is a new version of A0, which resulted from a write operation in property P. And with this information is where we avoid going back and forth between all of those program representations. This simplification is extremely useful when detecting, for example, prototype pollution vulnerabilities, which need to take into consideration subsequent writes into the prototype chain. So let's see how we build the multi-version dependency graph for the example that I showed you earlier. And for this talk, I'm only going to focus on the structure of the objects, leaving out the dependencies, but you can find the algorithm in the paper. So first, we are going to add an object for each function parameter, which are going to be the sources. In line 4, we have a dynamic property lookup, and so we will add the options node to represent the property of objects config, the object config. In lines 5 and 6, we have two property writes, which are represented by the consequent version edges on the graph. And then in line 7, we have a node to represent the call to the exec function, which is the sync. And it depends on the values of options.command and options.commit. So by looking here at this single graph, we can already identify the pattern. So options.commit is a property of the options object, which is a property of the config object, which is controllable by an attacker. And essentially, the main insight of our multi-version dependency graphs is that they capture how the objects evolve over time as its properties are looked up and updated. To evaluate the effectiveness of these multi-version dependency graphs, we built GraphGS, which is an MDG-based static vulnerability scanner to analyze vulnerabilities in Node.js applications. And it follows the same structure of the code property graph-based tools. In particular, GraphGS detects the command injection, prototype pollution, code execution, and path traversal vulnerabilities. We used Neo4j as the graph database, and we implemented the queries using Cypher. And the queries are very simple. They are entirely customizable, and they can also be extended to support other things. Our evaluation focused mainly on answering these three questions. So how good is GraphGS in detecting these vulnerabilities? What are the performance gains? And can we actually find new security vulnerabilities? For this talk, I'm only going to focus on the first two. And to answer this question, we leveraged two datasets from prior work, Vulkan and SecBench, which we use as our ground truth datasets. And combined, these two datasets provide a comprehensive set of vulnerabilities, 603, with the distribution summarized here on this table. These datasets are representative of real-world vulnerabilities, but they also contain a great deal of non-vulnerable sinks, which allow us to measure the precision of our tool. So to assess GraphGS's effectiveness in detecting vulnerabilities, we ran both tools, GraphGS and ODGen, in our ground truth datasets. We measured the recall in the first column and also the precision in the second column. And of course, the higher both values, the better. By looking at this table, we can see that GraphGS was able to detect 82% of the reported vulnerabilities, which is 63% more than ODGen, which only detected half of them. And we can also see a big improvement in the prototype pollution vulnerability, which is largely due to the fact that since we are building simpler graphs, we were able to finish the analysis more times and therefore find these vulnerabilities. To measure GraphGS's performance, we first measured the time that each tool took to analyze a package. And here is the cumulative distribution function of the time that, to finish the analysis. By the 10 seconds mark, we can see that GraphGS was able to analyze 95% of the packages, where ODGen flatlines at 70%. And therefore, GraphJS was able to analyze 37% more packages than ODGen. Of course, we also measured the size of the graphs generated by both tools. So in the first row, we have the size of the graphs generated by GraphJS, our multi-version dependency graphs. And in the second row, we have the size of the graphs generated by ODGen. We can see that the multi-version graphs are smaller than the graphs generated by ODGen. We only have 14% of the nodes and 42% of the edges. So there are many things that I did not cover in this talk, such as the full syntax of the graphs, the formalization of the analysis, and the soundness guarantees. But I invite you to read the paper to learn more about those details. So to conclude, I presented you multi-version dependency graphs, which is a new point in the design space in the code property graphs for JavaScript vulnerability detection. These multi-version dependency graphs are simpler. They have formal semantics, and they allow for simpler and more efficient queries. With GraphJS, we were also able to identify 49 previously undiscovered vulnerabilities, which actually resulted in 3 CVEs. And so with that, I finish my talk, and I'm ready for questions. Thank you.
Questions, come up.
Hello, thank you. Very interesting talk. I was just wondering if you could elaborate a bit more on the security properties you're checking, because the example that you provided, you could do this with a PDG alone, given that your taint abstraction or your data flow abstraction is sufficiently precise, either through access path if you just denote a JavaScript object as base object plus fields, or using collection modeling if you constructed map style. So I was wondering whether you have an example where you really show that you need the versions and what the cool thing about the versions is.
So actually, the example that I show is more complex. I only show the taint side vulnerability for the sake of the talk, but in the example, we actually also detect a prototype pollution vulnerability. And to detect this prototype pollution vulnerability, we really need these version edges because we need 2 subsequent writes in the prototype chain. And so here we can see that, for example, we have a new version of the options with a property. And then we also have a new version of this new object with another property. Actually, I think it's missing. Oh, no, yeah, that's right. And so if we don't have these version edges, what we needed to do is to go back to the program dependence graph and see what were the objects involved in this pattern and see the order of the operations. And then we needed also to check the syntax. And so the queries are actually very complex because they need to go back and forth all of those program structures. And here we only need to do one graph traversal.
I wonder if you have a normal data flow analysis that is flow sensitive. And for that one, where you just look at the command execution, that should be enough, I guess, if I'm not missing anything. If you're talking about prototype pollution, then I wonder if your data flow abstraction is precise enough and your analysis is flow sensitive, then you should not necessarily have to go back and forth, maybe aside from aliasing.
I mean, if I understand correctly the question, if you look at the multi-version dependency graph, it's pretty obvious that the options.commit is a property of options, which is a property of config. But for example, if you rely on the abstract syntax tree, you need to reconstruct this structure at the same time as you're seeing the dependencies. So it's a bit more complex.
I'm talking about a monotonous framework you just propagate forward.
Okay, more discussion on this point will follow. We have a long list of people behind. There's time after the session, please.
Hi, thank you. It was an excellent talk. I'm wondering how you handle function calls, in particular higher order functions, like functions get passed around a lot in JavaScript. I was curious how your representation and framework handles that.
So we leave most of that logic to the query stage, where we are able to reason about function calls and the interprocedural aspect of the analysis. Here we mainly have the nodes for the calls and associated with the arguments that they have.
Okay, we can take it offline. Thank you.
Thank you for the nice talk. I'm a little curious about what's your threat model what you use when you collect the data set on the real-world NPM packages, and what's the entry point you want to use for start this tail analysis like past travel. So even you think the exported functions as an entry point, there are still some functions like the functionality is just running some command or just perform some circle queries, such as some circle drivers. So how you can just query to say there's a path from the parameter to the sink, but the function functionality is just do the stuff.
So are you asking like if the package offers that as a functionality?
Yeah.
Yeah. So when we analyze the reports on the real-world data set, and we check them manually. So first we checked whether there are true or false positives with manual exploits, and we excluded the ones that were the intended functionality of the package. So I actually have here a table. Yeah. So for example, we found 101 exploitable vulnerabilities, but only 49 of them were unreported and not unintended functionality of the package. But we needed to do that manually. We don't know the domain.
Okay, thanks.
Thank you. That was a great talk. I was curious about so you detect 82%. Is there a pattern on the vulnerabilities that you don't detect? Is there like a specific kind of complicated structure that the analysis misses?
I mean, most of the things were JavaScript things that we didn't, I don't know the word. We didn't put them in the graph, so we haven't modeled them. For example, since these applications rely on third-party packages, that there are packages that iterate the objects for you, and so we don't have that logic in the code. We don't do inter-package analysis, and so we lose a bit of that information.
Thank you.
All right, thanks again. Now we are switching gear. The next talk, the speakers couldn't be here, but they can be online, so we'll take an online talk, provided that we are in contact with them. Let's see if we can, the AB team will do their magic. He's there, okay. So Joao Rivera will give the talk, and we can see you. We can see you, you can begin. Oh, but I think you're muted, are you? Maybe the AV team is working on unmuting you. So Joao, just give it a second. And hey, Joao, I know you're speaking, but please get ready to start over. Oh, it's pre-recorded. He's not live? What a disappointment. Okay. But you'll get audio on there. Do you know if they're going to be able to answer questions afterwards?
For instance, for some reason, we want to prove that x and y are both not equal to 1 in the nested ifs. And since this point is just outside the feasibility region, then we have guarantees that this is never going to happen. So there are many different numerical abstract domains that have been proposed in the literature. One of the first ones, and probably the simplest one that you can have, is just the bots domain, which only keeps, instead of keeping just the constraints of the values of the variables, it keeps the upper and the lower bounds of each variable. That's why it has like this box shape. And one of the most expressive ones is the polyhedral domain, that it really takes any linear constraint that you can have between variables. And between this very simple and very fast thoughts domain and this very expensive polyhedral domain, there are many abstract domains. For instance, zone, octagon, TVPA, and octahedron. And what this talk is about is about this TVPI, which basically stands for two variables per inequality abstract domain, meaning that in each constraint you only allow two variables to be in the constraint itself. Not like in the polyhedral, where you will have like arbitrary number of variables in each constraint. Okay, so let me go back to the previous example that we had before, but now assume that x and y are double precision floating point variables instead of integers. So what would happen for this case? Well, at the beginning it's just the same. X and y can take any possible values in the domain of double precision floating point numbers. But once you go a step further in the program inside the first if condition, I mean, you are tempted to do the same as before, just adding this constraint in order to reduce the feasibility space. However, this is not sound for floating point programs. And the reason is that you have round-off error. This x plus 2 is not just x plus 2, it's s plus 2 plus some rounding function that you can have afterwards, because floating point has limited precision. And this is usually solved using round-off error linearization. What I mean with this is that instead of just having the constraint with x plus 2 in this case, you would multiply this operation by this gamma. And this gamma is just a very, very tiny interval around 1, which models the round-off error that you can have. And this is not sound. This constraint is not sound. And if you were to plot it, it would look more or less like this. So the limitation of the traditional integer abstract domains is that they cannot really represent these kind of constraints, because these constraints now have interval coefficients for the variables, whereas the traditional ones only allow for a scalar coefficient. Also, you can see it slightly in the picture, but that also having these interval coefficients allow for non-convex shapes. I mean, you can see it a little bit, the non-convexity in the shown plot. Also, usually the abstract domains are implemented using rational arithmetic, and we aim for a fast implementation using floating point arithmetic in the implementation itself. So in order to do this, we propose a new abstract domain, that we call TVPI-FP. And TVPI-FP, what it does is the same concept as the TVPI domain, two variables per inequality. However, we allow interval coefficients to occur in these inequalities, in these constraints. And here you can see just an example of how two inequalities would look and the feasibility space that they would show. Some of the features of our new abstract domain is that it now can model these non-convex shapes that are common due to round-off errors in floating point programs. We support common operators for program analysis, such as join, meet, widening, inclusion test. We also support elementary functions, which are common in floating point programs, and these symbolic values, such as nans and infinities, in our abstract domain. And last but not least, we implemented it using floating point in its implementation itself, in floating point with interval arithmetic, to allow for a fast implementation. One of the main challenges when implementing and when designing this new TVPI-FP abstract domain is to handle in a sound way the non-convexness of the intervals inequalities that we allow in the operators, because now we have inequalities with interval coefficients. So for example, just in the join operator, just as it's done in the standard integer TPI, is that if you have two polyhedral and you want to compute the join, you first translate into their generator representation. And the generator representation is just translating the integral coefficients into a representation of only vertices and arrays. In this case, there are only vertices for both polyhedral. Now, over these two sets of vertices, you can compute a convex hull. You can identify the vertices that are part of the convex hull, and then you can convert back these vertices back to inequalities, to constraints, basically. And this works properly for the integer TVPI. However, for TVPI-FP, for the one that we propose, there are cases where the convex hull would not yield anything, like any constraint, because the shape of the joint is non-convex. For instance, if you have these two polyhedral, I mean, you can see that there is no convex inequality. There is no inequality with the scalar coefficient that could include these two polyhedral. So in this case, we modify the algorithms of the original TVPI, or we adapt them to handle also, or to compute also, holes that are not necessarily convex. In this case, for this particular example, I mean, we can just compute the join by adding an inequality that covers P1 and P2, and this interval inequality is not convex. And another challenge arises due to using non-interval arithmetic in our implementation of the operators. So this happens when performing an interval comparison, for example, and this comparison has an unknown state. What I mean with an unknown state is, for example, if I do this operation, just the interval between 0 and 2 is less than 1. Clearly, there is not an answer, a true or false answer for this, because 1 is included in the interval itself. So the left-hand side is not less than, neither greater than 1. So I will give an example of where this occurs in our implementation. So in the algorithms, we compare a lot the angles of the inequalities. And for example, when you have this inequality, just y less than 2x, and this is the feasibility space, then the angle is just based on the x-axis, and you can calculate it just with the arctan of the coefficient of x for this particular inequality. So this angle is 63 degrees. However, this is using scalar constraints. Once you have interval constraints, if you repeat this process, you would get the arctan of an interval, which will give you an interval of angles. And these angles are between 27 degrees and 63 degrees for this particular interval inequality. So what I mean with this is that not only we have interval inequalities, but when calculating, performing the algorithms of the operators with these interval inequalities, we also arise with interval angles of these interval inequalities. And the reason why I mentioned this is that this occurs, for instance, in our join operators. When we calculate the generator representation that I mentioned earlier, there is one place in the algorithms where we compare the angles of two inequalities and we check if the difference between them is larger than pi. If they are, then we decide whether to add a vertex or if we should add array for the generator representation. And in this case, if this comparison yields an unknown state, we have to make a decision. And we have different ways to handle this unknown state. And the first one that we try to do is to make a decision that preserves soundness. For this particular example, adding array is sound instead of a vertex. So this is what we do in the highlighted blue statements in the code. Another possibility is to evaluate using this joint representation. So I will not go into this part further, but this joint representation is a way to translate an interval inequality into 4 scalar inequalities that form a disjoint between them. And finally, another way to handle these cases when we have unknown state is just to drop the problematic constraint that is giving rise to this unknown state. And dropping constraints is always sound, but we try to avoid this as much as possible because we lose precision the more we drop constraints, of course. Okay, we go now into our evaluation section, and we compare TVPI-FP with other tools to analyze floating point programs. In particular, I will show the results against bots, DAISY, and Fluctuate. And Fluctuate uses the sonotope domain, whereas DAISY uses the box domain, but it also incorporates SMT solvers in order to shrink even further the ranges of the variables. All of them support elementary functions. DAISY only partially supports branches and loops, whereas we are the only ones that really truly support non-convex shapes. We do experiments with 62 benchmarks, where each benchmark is just a function that specifies ranges of its inputs arguments, and it returns a floating point result. And the accuracy we determine using what we call the improvement factor, where that is basically the range returned by bots in a benchmark divided by the range of the tool. So basically, we're using the bots domain as a baseline to determine how much to improve compared to the bots domain. So an improvement factor of 2 simply means that the range is half of that of the bots domain. And in terms of accuracy, at least, we see that TVPI-FP achieves an average improvement factor of 1.46. DAISY, it uses SMT solvers, is slower, but it's more accurate with 1.65 improvement in average, whereas Fluctuant only 1.25. So all of them improve over box, of course, they are more powerful. But another interesting thing is that out of benchmarks that consist of branches and loops, we improve over bots in 80% of the cases, whereas, for instance, Fluctuant only improved for this set of benchmarks only in 29% of the cases. In terms of runtime, TVPI is way faster than DAISY because, as I already mentioned, DAISY uses solvers, so it's between 1 and 4 order of magnitude slower, whereas Fluctuate is actually faster, it's 4.6 faster on average. So in general, it's kind of a trade-off between accuracy and performance. And with TVPI, we position ourselves in a sweet spot between these two factors. And just to show the whole glory of our experiments, we also compare with other tools, but I think I just summarize like the most interesting bits of information. But you can see all the details in the paper regarding our improvements and the timings and how fast we are or slower than other tools. And thanks for listening. This concludes my presentation. And just as a reminder, what I presented is TVPI-FP, an abstract domain for the analysis of floating point programs, which allows interval inequalities. It is implemented using floating point, and it supports elementary functions. I presented also some of the challenges that we encountered when implementing and when we designed this abstract domain, and I showed an evaluation compared to similar tools in the literature. Thank you.
He can hear us, so you can clap. Okay, Joao, you are there. That's great. So anyone want to ask a question? Now he can hear us. And so come up and ask your question.
Hi. Fascinating talk. Awkward question. What about widening? Is there a useful widening algorithm for TVPI-FP?
Yes. Actually, we use the same widen algorithm as in the integer TVPI. Maybe the only difference in widening is that we cannot do some of the optimization that they do for integers. But basically, the high-level algorithm is the same as integer TVPI, which is basically if you want to apply widening, you just remove constraints that you know that are problematic for widening. So it's basically you lose a lot of precision, and that's why in some of the benchmarks where we have loops, we see that we lose a lot of precision from the beginning, and we don't see any much gain compared to bots, because widening is in general, I mean, just loses precision a lot. Yeah.
Okay, brilliant. Thank you.
Joao, you mentioned a whole list of benchmarks. In which language are those benchmarks written?
Yes, these are C benchmarks. We took most of them from FPBench, which is like a standard benchmark for floating point programs, and some of them are from previous papers also related to the topic.
Very good. All right. I think we have exhausted our questions. Thank you very much for participating online.
Yeah, thank you. So bad that I couldn't be there physically, but yeah, nice to be here. Bye.
Okay, so where do we have the next speaker? Come up? Yep. We're switching back to good old-fashioned way. The next speaker is Mathias Rode Laursen, and please go.
Audio good? Yes, perfect. Right, thanks, Jens. I'll primarily be talking about like points to and control flow analysis, so I think it's maybe like a good idea that we start there. Most of you probably know what they are, but just to be safe. So points to and control flow analysis in general are very essential analysis techniques, right, for producing approximations about a program's points to information, and thereby also approximating the control flow in a call graph. And it is a prerequisite for many other client analysis. So of course, this is something that we want to do, and we want to do it well, because a client analysis might directly, or it will, in fact, directly rely on the call graph, and thereby a more precise call graph will also give a better client analysis result, right? So we want high accuracy, and obviously we also want high scalability as well, right? So graphically, ideally we would like to take these two circles and completely overlap them, right? That's typically not possible. We have to over-approximate in some cases, and it turns out often we also have to under-approximate. And why is that? Well, I think we can all agree that static analysis is pretty difficult, and especially for a language like JavaScript, because JavaScript has this very, very dynamic object model, right? So if we look at this piece of code here, this is a so-called dynamic property write operation. We can think of it as a read or a field write operation, but where the field that we're writing to is computed dynamically. And so this is really difficult to reason about statically, right? Because we have no way of actually knowing which field that we are writing to. And so there are sort of like two obvious approaches to how do we tackle this. Well, we can try and be conservative and over-approximate all the possible values, right? That's sound, but it's highly imprecise and probably won't scale very well, because we get a lot of spurious data flow around the data flow graph, right? So another approach, which is the one that I assume that we're taking in this talk, and is what scalable analyzers do for JavaScript at least, is, okay, we can simply ignore these dynamic property write and equivalently the dynamic property read operations. That's of course unsound, because now we are missing some of these actual call edges because we're never modeling them, but at least it's scalable, right? We can actually get a result out of the analysis. Now, recent work has shown that the majority of unsoundness for JavaScript, or for scalable JavaScript analysis at least, arises due to these dynamic property accesses. And so the question that we try to tackle in this paper is whether or not it's possible to actually model them without sacrificing the precision and without sacrificing the scalability of the analysis. And we use some building on some other previous work, which is this work on determinacy. So it's been shown that variables and expressions that are used in dynamic property accesses for library initialization code, is, they are often determinate. And what it means for a variable or an expression to be determinate is essentially that it evaluates to the same value at each possible concrete execution, maybe possibly with respect to some calling context. But the main point to take away here is that a single dynamic execution suffices to reveal these determinate values, and in that case, they'll be the same forever, at least until the program changes. So a single dynamic execution gives us this information, and then we can use that in the static analysis. So for instance, for some particular calling context here in this example, we might have that method evaluates to get, and the object app is always the object from line 2, and the value that we're writing is always the function from line 5, right? Right, and this leads sort of like to our contribution, which is this two-phase algorithm, where phase 1 is a dynamic analysis that we call approximate interpretation, and the second phase is then an extended static analysis that uses the output of approximate interpretation as input. And this output, we call this determinacy hints, not determinacy facts, as what's been done in the literature before. And it consists of these read hints, HR, and write hints, HW. And if we look at this phase, approximate interpretation phase, the general idea is that we let the dynamic phase of the algorithm deal with the dynamic language constructs, right? So it's very difficult statically to reason about dynamic property accesses, but it's very easy dynamically because we can simply just observe what's going on, and then that exactly gives us the answers, right? So this phase generates these determinacy hints, and they look something like this, the sets at least, where HR maps locations of dynamic property read operations, into what possible values were read, and similarly, the write hints have the abstract allocation sites of the base object and the field involved, so that's the string, and then the value being written. As I've mentioned, like the key idea is that a single execution suffices to reveal these values, right? So this is simply what this algorithm does. It just executes the program code, and then it observes whenever we see an object construction, we collect the allocation site, we collect the location where this happened, and when we see these dynamic property accesses, we collect these determinacy hints. And this is something that could look like this, that the dynamic read operation at line 42, it resulted in the object that was initially allocated at line 12, or whatever. So this is like how these hints might look if you would write them out in text. Now, you might think, I said we just execute the code, right? How does one just execute code? Do we require any test cases to run? And the answer is no. This algorithm is completely automatic. So it needs no input other than the program you want to analyze, of course. And so to execute the top-level code for JavaScript, this is very easy. You can simply just require the module, and by requiring the module, you automatically get the top-level code executed. But of course, there are probably many functions in the program that are not just directly executed from the top-level code. And so to deal with this, we use a variant of forced execution to explore these functions. So this allows us to explore functions that would otherwise have been very difficult to reach because we would have needed some input that could actually exercise them. But now if we've seen the function definition, we simply queue it up and then force execute it. And this is also where the name approximate comes in, because now we have to approximate actual executions, right? Because a function might require some arguments, and of course we can't provide sensible values for all possible real executions, so we have to deal with this in some way, and similar for side effects, like we have to ignore those. So this is why we call it approximate. A key design choice is that we only force execute each function once. The basic idea is that this is very fast, right? If you're only doing something for a function once, then it's linear in the amount of functions. And it's sufficient for these determinate values anyway, right? Because no matter which input you provide, or no matter like the free variables in the function, a single execution for determinate values will give the same result anyway. And now I think it might be worth mentioning that because this forced execution approximates behavior, this technique is inherently unsound, and this is why we call these hints for determinacy hints. Just a small example, all the code is not relevant for you to understand. I'll try and guide you through the interesting parts. So let's say we provide main.js as an entry module for approximate interpretation. We start out by executing the top-level code, right? So in particular, we will execute this require statement, which will require this express.js module and execute its top-level code. And similarly, then express.js will load these two modules. And when we are loading the application.js module, in particular, we will execute this code here, which performs at least a sequence of dynamic property write operations. And so we'll collect the hints that here we see the object from line 30 was written to, so that's this app object, and the property might be get, for instance, and the value that we wrote was this object from line 32, which is a function, and I say object because in JavaScript, functions are also objects. The top-level execution continues. We call this function express here, which turns out to be the create application function. And while calling that, we call this mix-in code here. And now this piece of code looks very nasty. What it essentially does is it performs a sequence of dynamic property writes from the second, for all the properties in the second argument to identical properties on the first argument. But again, we simply model this by just generating the hints that, okay, now the object from line 12 was written to, the property was get, and and listen, and the values were the functions from line 32 and 36. And now, by having these hints, now we know that the object from line 12 has a property called get and listen, and that they are functions. That's exactly enough for us to reveal that this piece of code here calls these two functions down here. And even if the entry module was this express.js module, so we never actually called this create application, right? The top-level code would still make us see the definition, and then forced execution would still fetch it and call it. And because this function, because the execution of it is determinate, we would reveal the exactly same hints as before, and we could still reconstruct the call edges. Right, that's phase one. Phase two, it's a bit simpler, even though this might look a bit scary if you've never looked at a points-to analysis before, but this is just a standard Anderson-style points-to analysis for a small idealized language. And yeah, the details are in the paper. What's interesting to note here is that there are rules for dynamic or static read and static writes. I don't know if I can point here. Static read, static writes, but there's nothing for a dynamic property read and write. And we now add these two rules, which exactly model the dynamic property read and dynamic property write operations with DPR and DPW, which essentially just looks through the hints that were generated, finds the abstract allocation sites or the tokens, and adds those to the corresponding constraint variables. So it's conceptually very simple, even though it might look a bit complicated. We implemented this algorithm in Jelly, which is a state-of-the-art open source analysis tool for JavaScript. And the approximate interpretation algorithm, like 2,700 lines of code. And additionally, phase two only took like 200 lines of code to actually use these determinacy hints. And for our experimental setup, we evaluated this on 141 real-world Node.js-based applications. And for 36 of those, we had dynamic call graphs available. And then we used those as like a ground truth when comparing with the static analysis. So research question one, here we looked at the effects of the hints on the analysis accuracy. So the blue here is the baseline without using approximate interpretation, and then the orange bars are show the results when we use approximate interpretation. And for the left case here, we measure the increase in the number of reachable functions and see that we get an average of 21.8% an increase, which is quite nice. And for the cases where we have dynamic call graphs available, we can actually measure the recall and see how much of a recall improvement we gain, and we see that we get 12.2% increased recall. And of course, we also have to look at the precision. How does this affect the precision? And we have some other metrics for doing that. Again, when we have dynamic call graphs, it's very easy. We can just actually look at the precision. For the other 141 cases, we looked at this monomorphic call site, but you can read the details about that in the paper. But yeah, as a conclusion for this, approximate interpretation does successfully reduce static analysis unsoundness, and it does not, without significantly harming the precision of the analysis. And for research question 2, we look at the running time of the dynamic phase and then the performance overhead of the static phase. And we see for the running time of approximate interpretation, this averages to 4.5 seconds. So it varies between 0.6 and 51 seconds per program, which seems very reasonable. And for the overhead of the static phase, for the majority of the cases, the running time is increased by less than 10%. And for only 20 out of the 141 cases, do we see a larger than 2-factor slowdown. So we conclude here that approximate interpretation is indeed scalable to real-world applications. And this concludes my talk. So I've talked about this two-phase hybrid and dynamic static analysis algorithm for modeling dynamic property accesses, where we use the dynamic phase we call approximate interpretation that produces these determinacy hints and utilizes forced execution to explore larger parts of the program. And we've shown that these determinacy hints can easily be integrated into an existing state-of-the-art static analyzer tool. And our experiments show that the algorithm is scalable and significantly improves the call graph construction for real-world JavaScript programs without significantly harming the precision. That's it. Thank you.
Questions? We have a microphone. Come on.
Thanks for the talk. This is Manas Thakur from IIT Bombay. The question I have is, when you use the hints to perform some analysis and probably some transformations later, do you detect if the hints have gone wrong in future?
No. So the dynamic analysis, as I mentioned, might produce. I don't know if I mentioned that, but as I mentioned that it was unsound, right? So it might produce hints that are not actually true, and this would lead to a loss of precision in the static analysis, right? Because you would add some spurious edges, because this hint would show something that was not true, so you would add a spurious edge. We don't do anything to try and detect whether or not this is the case, because that would be very difficult. Then we would have to actually see, well, what could the dynamic property read or write operation actually evaluate to, and then we'd be back at square one, basically.
Yeah, well, we do it in another context, not dynamic property reads. So let's talk offline more.
Yeah, sure.
Hey, nice talk. So you said that when you do forced execution, you ignore the side effects, but that would be like wrong in some certain cases, right? Like if it's a function which does something like a CRUD call or a writes to a database, then you are basically doing a null execution. So how could we actually ignore that? Like,
like we provide, when we do forced execution, we provide some arguments for the call that can sort of simulate, or not simulate actually what's going on, but you can have a function call to an argument and the program doesn't crash, basically. But the forced execution would, like we've also made like some sandboxing. So for instance,
okay.
you said something like accessing a database. We have a sandboxing environment that makes sure you cannot connect to any database or like go over the internet. That's also important, right? Because we're executing arbitrary code. So, I mean, if some guy just wrote some dangerous code and said, use this algorithm on it, then your machine is all of a sudden infected, right? So we have a sandboxing mechanism for handling such cases.
And the input arguments are like mock arguments, right?
Yeah, it's just like the JavaScript proxy mechanism.
So one more question I had was...
Could we move on to the next question, please?
We can discuss offline also.
Sure.
If,
Really, thanks for the nice talk. So you have to make some choices in doing the forced execution. How can that, so to what degree can that affect, precision or whatever?
I mean, yeah, you have to do a lot of choices. So first of all, like the order of when you force execute things could actually matter, because like one function might, two functions might use a global variable, and one function does something with it, and then another one does another thing with it, right? And so that might, like the order of execution might depend, or the result might depend on the order of execution. And similarly, for like to ensure that things are not running for an indefinite amount of time, we also have some options, such as like if the call stack gets too large, we immediately cut off the execution of this function, and we don't allow long-running code. Of course, larger bounds would mean that we can analyze for longer and then maybe get more hints, but yeah, it's a trade-off.
Cool, thanks.
Final question of the session.
Try to make it quick. Thanks. This is really great work. I was wondering if you actually observed in practice any hints that were unsound. My intuition is that almost always they would be feasible. So I was wondering if you saw any patterns around that.
I don't think we actually observed, like we made some toy examples where of course we could get unsound hints, but in practice it's not something that we actually had to deal with.
That's great. All right, thanks to the speaker again. And we have one more talk.
Okay.
All right, so this talk here is given by Arjun Pichanathan, please.
Hi, I'm here to present Falcon, which predicts the cache performance of a given program quickly, accurately, and incrementally as you update a program. Okay, so why do we even want this? Well, I mean, if you want to optimize some program where, let's say, there's some two kernels that the input goes through, and you're considering like which of two optimizations to apply, like maybe either fusing or tiling, you need some kind of cost model which allows you to pick the better one. So many optimizations focus on memory performance. So in this paper, we focused on that. And yeah, maybe if you could somehow predict what the miss rate would be, cache miss rate would be after applying each of these, then maybe you could pick the better one. And in particular, we want to focus on analyzing the cache performance of huge programs, like let's say neural networks. They have like many different phases, and each of so here we have what's called connext neural network, and each block inside it has like a bunch of additional kernels, and like let's say you want to optimize one in particular, and you want to ask like, okay, how does this change performance of the whole thing? If you had to run this whole like forward pass of connext in the large setting, like profiling it takes like 70 minutes. And you would hope to do it much faster with analytical modeling, but the state of the art cannot scale to these huge programs and actually ends up being slower. But we are able to do it pretty quickly, and that's what we'll go into now, how to do that. So we model LRU caches. So least recently used cache. So I'll quickly go through what it is. I assume people are kind of familiar with it. But yeah, as you access A, B, C elements, these elements come into the cache, and when you access an element that's already in the cache, then it sort of comes to the front. And if you have to get rid of some element because the cache is full to insert a new one, then the one that was accessed least recently will get eliminated. And that's it. That's what a least recently used cache is. And you can sort of like analyze this. So the elements that are in the cache are always the last n that you accessed, unique locations that you accessed, and here like the size of the cache is 3. And yeah, a miss occurs in exactly one of two scenarios. One is if you access something for the first time, so that's called a compulsory miss. And the other is if you did access it earlier, but the last time was a long time ago. And what do we mean by long time? The sort of metric that matters here is how many unique memory locations have been accessed since the last time that the same location was accessed. So here it's 2, and the cache size is 3, so it's a hit. But if it was 3, with a cache size of 3, then it's a miss. And the way the model is going to work is by sort of creating an analytical formula that models this distance. Okay. The state-of-the-art model, how they did it was they sort of computed these dependencies because we had to find the last time the same location was accessed. That's basically a dependence. You don't have to worry about these formulas. But basically, like what I want to tell you is that they used all these like sort of operations to create some kind of formula which captures the dependence. But unfortunately, when you do these things, it doesn't scale very well with the size of the input formula that you give. And therefore, if you want to analyze a very large program like say a neural network, then this stuff doesn't scale very well. So that's what we want to focus on, how to scale this. So actually, like what we want to do is just dependence analysis. So we use like the existing algorithms for polyhedral dependence analysis, which can give you the same result, but much more efficiently for large programs. So let's look at an example. Here, like for 0 to 499, we're accessing A at I, and then B at I, and then C at I, and C again. And then C at 0, B at 400. And A at some X, let's assume it's like something you don't know, but it's in bounds. Like I'll tell you why we need that later. But anyway, so you just run like a dependence analysis algorithm on this thing. It will tell you immediately that like all the accesses in the first 3 loops have no dependence. So it's like a compulsory miss because they're accessing those for the first time. And if we look at this C0, we will get a dependence to this statement at iteration 0, and then B to iteration 400 of that loop, and A, we would get a dependence to some iteration of the first loop. And I won't go into the details of how to sort of compute the distances and so on, but basically you will get 499 unique memory accesses between C0 and iteration 0 of that loop. So that 499 is the distance, and let's assume that the cache size was 512. Then this would be a hit because 499 is less than 512. For B, it would be 500 because of these loops. Both of these loops combined access only like 500 unique elements because C is repeated. And then iteration 400 of that loop has 99 after it, so 599 in total, which is more than the cache size. So you get a miss. And the interesting part here is for A, even though like we don't know which location is accessing, we still know it's going to be a miss for sure. Because like we have the B and the C loops in between, and even if you don't really look into which iteration the dependence goes to, you still know that there's at least 500 plus 500, so 1,000 unique elements accessed in between by these loops, which is more than 512, so it's a miss for sure. And this is what we're going to exploit to do some optimizations here. So even if I change this last first loopness at the top to maybe be in reverse or add some other statement or whatever you do, it doesn't matter. It's always going to be a miss. So we don't even need to look at that loop nest. So what this means is when we're doing this kind of dependence analysis, that if there was some dependence that was really far away, then in general dependence analysis, we would have to go all the way there to find out what the exact dependence is. But here, because in this particular application domain, we only care about finding out whether it's a hit or a miss. So we want to find out if it's near or really far. And so that means that in a practical program, you only really need to look, like a couple of loopness above for each sink, for each statement that you're trying to analyze. So that's one optimization. And this kind of principle will immediately also lead to being able to do incremental updates of the analysis. Because as we just saw, no matter what changes we do to the first loop over there, the last statement is always going to miss. So what does that mean? Let's say that the user made some kind of modification to this first loop. Then we can sort of start computing this distance metric downwards. So after this, for B loop, there's 500 unique accesses. After the C loop, there's 1,000. And we know that this 1,000 is greater than or equal to 512. And that means that everything after this sort of line in the program is always going to have the same cache performance as before, no matter what modifications you do to that first loop. So now that means that if you change that loop, then you only need to recompute results for the next two loops after it. And the whole rest of the program can just inherit the results that you computed earlier. So here, for example, in the C loop in the gray box, its dependence goes to the C loop right above it. And so its distance is not in any way affected by the modifications that you did to anything above that. And similarly, the C0 also has a dependence in the unmodified region and also the B400 axis. So since all of these dependencies and distances are sort of within code that is the same as it was initially, they're going to have the same cache performance as before. Now, the A thing is a little bit different. It does have a dependence potentially in a modified region, but it doesn't matter because, like we saw earlier, it's too far away. So it's going to be a miss no matter what you do in that loop. So basically, if you modify the first loop, you only need to recompute results for the modified loop, of course, and 2 more loopness after that. So that means that, again, in practice, sort of like there's like a constant number of loops that you have to recompute for, which means that it ends up being much faster than it would be to compute for the whole program. Okay, so now let's look at an experimental evaluation of the performance. So the previous models had always focused on what's the polybench benchmark, which has many small programs. So each is like basically one loop kernel, maybe matmul or Floyd washer or something. They have like sort of complex code structure, but the size is small. And that's the reason that these previous tools like didn't really need to think about scaling. So we made a new benchmark consisting of like convolutional neural networks, like standard ones like AlexNet and ResNet and many others. And sort of like these neural networks are much bigger than like the single kernel benchmarks. And because of that, they like being faster on these requires like different optimizations. And we saw that the previous state-of-the-art haystack is actually like really slow on many of these huge networks. So this is a linear scale, it's hard to see, so let's make it log scale. And so Falcon runs in less than 5 minutes on all of these, whereas we run with like a 4-hour timeout because otherwise, it takes forever. So haystack hits this timeout very often, and we always run within 5 minutes. And because the dependence analysis thing that I just talked about is sort of separate for each statement, so it's like embarrassingly parallel and you can trivially parallelize it, whereas the haystack approach of sort of computing those operations on the formulas is not as, cannot really be parallelized. So with parallelism, we get even more speed up. And for to evaluate the incremental computation, we sort of like look at an average across the program of, we look at each statement and we consider if this were updated, then how long would it take to recompute the analysis incrementally. And this gives like a further 100x, actually 133x speed up beyond recomputing for the whole program. And on top of this, we have some improvements to accuracy as well. So the way haystack worked is there's some approximations made to like sort of simplify the analysis and make it practically feasible. So if you had to figure out, so until now I've been talking about elements being in the cache, but actually in practice you have what are called cache lines, and each cache line has, let's say, 8 elements. Then to find out which cache line is hit by some array access, you have to basically do this computation. So the base address of the array plus, like the linearized access expression. And then you need to float divide by 8 because there's 8 elements in each line. And this float division and this expression is kind of complicated, and so it can end up being slow in practice. So what they do is sort of do some kind of padding where firstly let's assume that the base address is aligned, and now sort of pad the last dimension so that the expression simplifies. So once you pad one of the dimensions, then everything else becomes a multiple of 8 and it goes out. Basically, they sort of have to pad the last dimension to 8. And that seemed to work okay for them in polybunch maybe, but like in convolutional neural networks, for example, and probably many other applications, the last dimension can be really small. So if you pad it to 8, then it makes a big difference. So we may do a slight modification to this where we look for a sufficiently big dimension and pad that. And that actually makes a pretty big difference to accuracy, at least on the benchmark of CNNs. The previous approach had a correlation of around 0.56 to between hardware measured cache miss rate and the predictions. And for us, we get 0.98, which is, I would say, pretty accurate. And yeah, so to conclude, Falcon is fast, more accurate, and can incrementally update computations. Thanks.
Very good, thank you. Questions, come up to the microphone.
Hey, it was a really nice talk. So I had a question. So you said that the analyzed cache properties are inherited by the blocks below. So like how do you do that? Like you look at the dominating blocks and only inherit for those blocks, or it's more like based on control flow?
Yeah, so we didn't go into those details here because the benchmark is like sort of straight line code with just loopness. So
okay, you don't
yeah,
need
we just
to
literally look at it like serially below in this.
And in the loopnest, if the iteration counts is unknown, like the trip count is not known, so in that case,
it
will
has
it still
to be
work?
known.
Okay, it has to be.
It has to be known. I mean, in the neural network benchmark, like the sizes are fixed and everything is fine. So
okay, so it's
if it's not known, then you can't do it.
Okay, thank you.
And neither can any previous model either.
Okay, thank you.
Well, you mentioned Falcon is multi-threaded, but do you consider multi-threaded programs? Do you assume the cache may be polluted by other threads? I mean, do you model it?
Oh no, we can't model multi-core. Like we can't model shared caches.
I see.
Single core.
Are there existing works that do it? Are you aware of?
Not, at least not in polyhedral models. Like it's really hard, and it's also non-deterministic. Like so, yeah.
Nice talk. How much did the hardware prefetching interfere in your evaluation?
So the measured miss rate is for a PMU event, which is basically we are trying to. It only refers to the L2 accesses. I think that the prefetching is not counted in that event. Right? That's what I believe. Yeah.
Thanks for nice talks, and I have some questions from the implementation aspect. And because during the compilation, the compilers may do some like loop unrolling and instruction reordering to improve the performance. And I would like to know if the analytic model is still applicable after the interactions done by the compiler, and what's the interplay between the analytical model and the compiler's optimizations?
Yeah, so we implemented this in the MLI framework. So like you would have to, you would have to give the model the program after you've done the optimizations. So I don't know if that answers your question, or what is your question?
Yes,
Okay.
Thank you very much.
Okay, thank you again.
Thanks.
Okay, and this concludes the session.
Everyone, so welcome to this last session, the second session on program analysis. It's really great to see so many papers on program analysis. So the first presenter in this session is Kotwood Stanju from Oracle Labs, who will tell us about scaling type-based points to analysis with saturation. Welcome.
Thank you. So yeah, I'm going to talk today about our work on fixing scalability issues of our points to analysis. First, a bit of context. Our problem domain, his whole program points to analysis for optimizing compilers. So we implemented this analysis in the context of the Graal VM native image project, which is a new Java VM that takes your application together with the libraries, JDK, and the VM internals, all written in Java, or some language that compiles to Java bytecode, and feeds all of them together to a program analysis, a closed world points to analysis, to prove facts about the code. And then the results of the analysis, we feed them into a ahead of time compiler. The results that we care about from the analysis are, first of all, the call graph construction, because of course we want to remove as much as possible of the code to minimize the size of the resulting binary. But we also want some specific fine-grained type information at certain program points to be able to do interesting optimizations, like call-side virtualization, null check elimination, or even removing types, fields from certain types that we know are unused. So in this context, what we need is a sound, precise, and fast analysis. I know, a lot of requirements. Unlike the analysis we heard about in the morning, ours needs to be sound because we cannot afford any false positives. Any false positive, it's imprecision in the compiler, which can lead to a crash at runtime. So we really want a sound analysis. It needs to be precise enough to justify the time you spent in the analysis for the entire compilation pipeline. So it needs to enable enough optimizations in the compiler, and needs to run fast. So this is part of a daily driver of many users that use this on their command line to modify their application a little bit, and immediately they want to see a fresh binary out of it. So we're talking about tens of seconds to maybe a few minutes, which in program analysis, it's quite fast. So why can existing analysis fulfill all of these requirements for us? First, on one hand, we have the context-insensitive points to analysis, right, which happens to be precise enough for our case, but can have a quadratic behavior in practice. So for a program with V variables and heap abstractions, where here for heap abstraction, I mean it's the static model of a dynamically allocated object at runtime, you get OVN complexity. Right? So for large enough programs, that becomes a huge problem. Unfortunately, most standard Java benchmarks like Spec, JVM, and Da Capo are too small to exhibit this behavior, but real-world Java applications have a huge problem there. On the other end of the spectrum, we have the rapid type analysis, which avoids this quadratic behavior because it doesn't need to model each variable individually. It instead starts with the set of reachable methods, finds what types are allocated, infers more reachable methods, and so on iteratively until it reaches an endpoint, and that solves the scalability problem. So you grow linearly with the application size, but you lose significant precision. So the question we asked ourselves was, can a context-insensitive points to analysis grow linearly with application size while still maintaining soundness and most of the precision? And the answer for that is yes in our case. So let me plot the analysis I just mentioned here. We're looking here at, on the x-axis, at the reachable methods after the analysis finishes and the compiler removes all the unreachable code. And on the y-axis, we have the analysis time. For the rapid type analysis, of course, we see the expected linear behavior. Here we're looking at 7 benchmarks from various sources, the biggest applications we could find. At the very right, it's Renaissance benchmark suite benchmark based on the Spark framework. Then the 3 bigger ones in the middle are 3 modern Java microservices frameworks like Spring, Micronaut, and Quarkus. And then to the left, there are a few more benchmarks that are representative and we extracted from related work. So then when we plot the points to analysis, you can already see the problem starting at about 100K, right? And then, the more you have to analyze, the bigger it gets. Here we have like almost like 5x difference for the biggest benchmark. Here it's important to notice that the lines on the points on these lines are a bit to the left in the case of the points to analysis, because of course the points to analysis has better precision, can prove more unreachable methods and remove them from the graph. And then the last line, it's our analysis. Our analysis has the same linear behavior as the rapid type analysis, while preserving most of the performance of the precision, of the points to analysis. So then we call this analysis a type-based points to analysis with saturation. So what does that mean? So first of all, we use a type-based analysis, points to analysis. Unlike traditional analysis, we don't take into account the specific allocation site of an object, we just care about the type. The type is essential to enable optimizations like call site virtualization, to maintain field sensitivity, and so on. But moreover, the call site is in general lost to, when you analyze Java features like unsafe and Java native interface, once you pass an object from the Java world to the native world, you lose all the precision, because for soundness reasons, you have to assume that all objects of the same type are aliasing. So you lose all this call size allocation size sensitivity anyway, so we remove it from the beginning. And the second step is using this idea of saturation for the variables in the points to graph. So the insight here is that if the compiler cannot use an analysis result to drive further optimizations, then the time spent proving that result is not really well spent, right? So in our case, we just want to preserve precision where it matters, just enough to enable these optimizations. So we track a small number of types for each variable. If you can prove that one variable has one type, that's great. You can do devirtualization, you can do type check elimination, and so on. If you have a small number of types, then you can still do some polymorphic inlining and so on. But then once you get into 10, 20, 200, 2000, it doesn't really matter for the compiler, because those results are virtually equivalent from a practical standpoint. So to go a bit more detail with this saturation idea, so what we do precisely, we set a maximum size for each type state, right? When you exceed that size, we just call it saturated. So then the points to analysis no longer needs to track concrete information for each of these variables, and instead we fall back to declare type information. This is information that we get from the compiler, from the source code. So then a saturated variable can have any reachable subtype of its declared type, right? So then when new types become reachable for that declared type, you get the precision for free for that variable. You don't need to analyze that variable independently anymore. So this is what, the declared type information fallback is what allows us to preserve most of the precision. And the second, once a node in the pointer assignment graph gets saturated, then you can simply remove it. And then more importantly, you can propagate, and you have to propagate for correctness, this saturation signal along all the use edges. Because all the dependent nodes, they cannot rely on the saturated node to give further analysis types in the analysis, which has the side effect that reduces the size of the graph quite a lot while the analysis is running. So you reduce analysis time by not having to analyze as much anymore, and you reduce the memory footprint of the entire analysis. So then, if we go back to talk about complexity, now we're looking here at complexity of a type-based points to analysis. So the second variable this time is types, but it's still quadratic in practice. Now with saturation, the second variable becomes a constant. So your complexity becomes linear in number of variables, so application size. So all of a sudden you have a nice algorithmic property of the analysis that you can rely on. I'm not going to cover the formalism of the analysis, how saturation fits with the traditional analysis. That's all in the paper. But instead, I would like to look at the code example here. So here we have a simple main class that has two objects, O1 and O2. Each of them returned by two source methods, source 1 and source 2. And then on each of them we call toString. ToString in Java, it's a method declared on the base type. So it's on the object type, which is the base type of all the other types in the system. So these two call sites have the potential of being highly polymorphic. So then source 1 always returns an A and implements toString. Source 2 loads a value from an object array and returns that to its caller. So then, yeah, we parse this code. We build our type flow graph, where each node in the graph models one of the operational objects. They are linked with use edges that propagate type information to their successors. And yeah, the new instance node is a source of value, of type in our case, in the analysis. So source 1 and source 2 methods are immediately resolved statically. So they are immediately linked into the interprocedural graph. And then when we analyze new instance A, we propagate that type information along the use edges all the way to this virtual call. And here we can resolve the concrete callee A toString. We link that in the caller, the parameters and the return type, and propagate the type further in the in the callee and all the other callees. And then we propagate the return type back to the caller. So at the end of this phase of the analysis, we can already prove that O1 has a single concrete type, which is A. Using that information, we can eliminate this implicit null check. In Java, all the visual method calls have an implicit null check. So here we track nullness information, so we know this can never have a null pointer exception at runtime. And moreover, we can simplify this virtual invoke. We can optimize it to a static invoke or direct invoke because we know that this is the only callee possible at runtime, right? That can in turn enable some inlining of this method and so on. But now, when you look at the second half of the example, things get a bit more complicated. Unfortunately, in Java, object array, it's a huge source of unpreciseness for analysis because most collections use an object array internally, and objects array are going to alias in practice unless you use a very, very deep context in your analysis, which is not really practical. So when that happens, most likely the value you get out of here has a huge type state, right? It's going to have thousands of types in a big enough application. So that means this value is already saturated from our point of view, which means that, yeah, we mark it as saturated, and we propagate that signal across the use edges all the way to the virtual invoke, and all these nodes are now removed from the graph. But then what happens when you remove a virtual invoke from the graph? Well, for correctness, you have to add in place another construct, which in this case, it's a global per application virtual invoke that models all the virtual invokes that were saturated on the same target method. Right, so then this is linked to all the possible callees at this call site. It transmits all the possible types, back to the return of this method, which maintains the soundness of the results of the analysis. So after this second phase of the analysis, unfortunately, O2 cannot be optimized. You cannot prove anything about its type, but you don't waste time in the analysis trying to do that by propagating types here continuously. So we simply cut off this part of the graph and continue the analysis in other parts where it's more productive. Here it's interesting to notice that although the formal receiver can saturate, the type checks inside toString method can actually allow the formal return to still maintain its precise type information. So saturation propagation across use edges stops where you have enough filtering information. And then as the last thing I want to cover is one of the results from our benchmarks in more detail. I'm using here Spring Pet Clinic. It's one of these microservices frameworks from Java, which only has 200,000 methods. So it's not our biggest benchmark, but the performance profile, it's a bit nicer to look at because there is not such a huge difference between the numbers we get and the default numbers. So I plot here the rapid type analysis and then the context-insensitive type-based analysis with saturation between 0 to 2048. A context-sensitive analysis for looking at the performance, but we also measure a context-sensitive analysis. Here we don't care about the time because, of course, the time goes out through the roof But what we care about is the precision, like what would be the best precision we could get with the best analysis we can implement. This one is a standard 2-object, 1-heap analysis from the literature, which is implemented in the same framework. So then for the metrics we care about, we actually look at the compiler results after applying the analysis results, right? We don't immediately look at the analysis results because what's more interesting for us is, okay, what can I do with these results? So we look at type checks, also null checks, polymorphic calls, and the call edges, how big is the graph after the compilation. Here for type checks and polymorphic calls, we don't have the numbers for the rapid type analysis, but if you set a threshold of 0 for saturation, you essentially degrade the points to analysis to a rapid type analysis in practice when it comes to precision. Performance-wise, you still pay a bit of penalty because you need to track your type flow graph initially. But here we can see that already in the first few hundreds of saturation threshold, we get more than 2x improvement in analysis time for this benchmark, while improving precision quite a bit in all the metrics that we care about. And one last point I want to make is that context-sensitive analysis, although you spend so much time when you want soundness, is not even give you that much precision. Because if you want to model unsafe Java native interface soundly, then you lose all that precision when you have to over-approximate, because you cannot ever afford to under-approximate. And that concludes my talk, and I hope we have time for questions. Thank you.
Yes, questions, please.
Hi, it was a really cool talk. I just had a question about your last slide. For type checks, what are those? Are those due to downcasts or array stores or just everything like that?
Everything, also the implicit type checks. In Java, sometimes you have implicit type checks, so not only the bytecode ones.
Like what's an implicit type check?
You can have a check cast. You can have and then you can have for field accesses.
Okay.
But it covers all the type checks.
It covers all the kind of dynamic type checks.
Yeah, exactly.
Okay, thank you.
Hello, very interesting. Would it make sense to do a quick pre-check whether you have any native method that you're calling? Because if you assume a program analysis framework that uses summaries to abstract from API behavior anyway, the only question is whether you have native code inside the user code, and then you could just check over it whether there is a native method declared or not, and in that case you wouldn't need that over-approximation anyway in the first place.
Sure, you could do that. You could have your type descriptors at native calls, but all in all, you're going to have some native calls somewhere. And because you have so much aliasing, you cannot prove that an object only, it's collocated in a certain part of the application. Most likely, it's going to escape anyway.
Yeah, I was just imagining if you're using summaries for the API calls, right? In that case, you're getting rid of all the JDK implementation anyway because it's stopped away for performance reasons. And then I could imagine that there are applications that just have no native code left at all.
That is not true. So in this project, we are actually putting together the entire JDK, which uses heavily unsafe and GenI calls, and yeah, that's...
I know that my model was slightly different, kind of. I don't have the JVM, I put that into summaries on models as well, so that I just analyze the application. Then I was thinking if I could use what you have presented and take it even a bit further because I can constrain my model.
Sure, but then you need to really model the behavior of the JDK in great detail unless you don't allow any object to cross the boundary between the application and your model.
Let's take this offline. There are approaches for actually summarizing JDK methods.
Yeah, so in that case, of course, yeah, you could improve the precision a bit. But in our case, yeah, we want the JDK to be analyzed together with the application. That's the whole point, to remove unreachable code in the JDK. Because at runtime, you want the minimal footprint and instant startup for your binary.
Okay, thank you.
All right, thanks for the nice talk. So it looks like here from these graphs, right, that the analysis time kind of is basically the same regardless of size, and then the precision kind of bottoms out, at 1,000, 2,000 for this particular benchmark. But would that vary depending on the benchmark, like what size you need to saturate to?
So there are all the details in the paper, of course. In general, we found out that the range for the saturation threshold is quite wide. As you can see here, already around here, you can get all the precision benefits for pretty much the same budget. So it doesn't vary that much. So, but what is constant in our benchmarks for the same size is this ratio here between a saturated analysis and a context-insensitive analysis that doesn't do that.
Thank you. All right, let's thank the speaker again. Oh, here it is. All right, next we have program analysis for adaptive data analysis. Go ahead, Waihaoku.
University, and okay, it works now. And first, I want to introduce some of the collaborators: Jawan and Marco from BU, and Deepak from MPI SFS, and Jonathan from Northeastern. So data analysis, it is designed to find some properties of some populations by getting some samples. And a good data analysis, it can draw some conclusions that generalize beyond the specific data samples. And in this area, people use the concept of generation errors to measure how well such models can predict the outcomes for these unknown, unseen new data from the populations. And the generation errors, it can be formally expressed as expected values over the distributions of these populations and of distance between the model's prediction result and the true labels via loss function. And normally, we want to have a low generation errors. And adaptivity, it occurs when the choice of the method to analyze the data set, it depends on the previous interaction with the same data set. So it happens when people they try to reuse the data set across different projects during collaborations, or when people trying to, in machine learning, they use the same data set for feature selection and regression, or in the regular exploratory analysis, when the data analysis, they trying to design which queries to run after they see the result of a previous query. And this adaptivity, it will cause high generation errors. To control these generation errors in adaptive data analysis settings, people restrict the data access to a query request. And here we only focus on the linear queries. And when these queries, they are sent to mechanisms will use some random process to make sure that the result of the queries does not rely too much on the sample data. And there are some mechanisms we can choose. For example, Gaussian mechanisms that add some Gaussian noise to the query result, or data splitting mechanisms that split the data into different pieces, and threshold mechanisms that set a threshold for different queries. And now, naturally, we want to see is, for a data analysis, what is the better mechanisms we want to use? So we focus on linear queries. So these generation errors of linear queries, it is related to the maximum of absolute values of the predicted result and the original result. And according to the theorems from DWalk, these values, it is related to 3 factors. The number of the sample data, n, the number of the query numbers, and also the number of rounds of adaptivity. And these first 2 factors is easy to understand. So we're focused on the numbers of rounds of adaptivity that can affect our choice of the best mechanisms for adaptive data analysis algorithm. And it's defined to be the depth of the chain of queries. So to illustrate this concept, I first want to introduce one example. I call it to be 2-round example. And suppose we have a classifier for population P, and we have samples like 400 attributes and 1 label. To simulate this in the adaptive data analysis, we can first run 400 non-adaptive queries, computing the correlations between attribute and the label. And then we can ask another query. I call the query for 1. It depends on all these previous correlations. In this way, we can have a graph, query graph, and every node is a query, and if we have an edge between 2 nodes, which means one query may rely on the result of another query. If we go back to the definition, the adaptivity is designed to be the depth of the chain of queries. In these graphs, we will have many chain of queries, and in different colors. In this case, all of the chains, it has the same depth too. So the adaptivity is to here. That's the reason we call it 2-round. And we do some experiment about these examples, and it shows that we fix the data size and change the query numbers, and show that in most cases, data splitting is usually a bad one. Even more further, if we change this program bit and to make every query to rely on its previous queries 1 by 1, then this chain the depth of the chain become much larger. And in this case, the adaptivity become 401. Our experiment shows that in this case, Gaussian mechanism is usually a bad one. Based on these observations, we designed a program analysis trying to statically estimate this upper bound on this adaptivity so that it can help people to identify which mechanisms we want to use and to control the junction errors in adaptive data analysis. To this end, we need to answer a few questions. The first is how to define the models for adaptive data analysis. So if we go back to the adaptive data analysis settings, first task is we need to design a programming framework so that it is able to express submitting queries to some mechanisms. And our choice is we have Y languages plus labels, and these labels used for tell people where this command it is. As for these queries, we add some primitives for the queries. And if we go deeper into these queries, we have query expression and query values. Here, we have a special symbol, chi here. Chi, it represents a row of the database. So chi A, it represents an attribute at index A of this row. Now we have these programming languages. We can express these 2-round examples in our languages. And the interesting part is at line 3, we have a query request. And we focus on linear queries, so this line 3, it means such a query request that compute the empirical means of the product of the J's attribute and the K's attribute. Now we are able to write some programs. We need to define what is adaptivity. So our semantic-based adaptivity, it is based on an annotated weighted dependency graph. In this graph, every node, it is labeled variables. And every edge, it represents a main dependency between these variables, which is tracked by the trace-based operation semantics. In this semantics, the trace is a list of events. And we have two kinds of events. The assignment event for this standard assignment and the query request, and the test event for like a conditional statement like if and while. We also have the query expression evaluation that will evaluate a query expression to its query values. Now, this may dependency between these label variables, it catches both data dependency and control dependency. So if we think, we say one variable A may depend on variable B, either means if we change the value of B, it may also change the value of A after B in the trace, or if you change the value of B, it may cause the disappearance of the A after B in the trace. If we go back to the graph and look at the node, we add some annotations to the node. So first one is query annotations. It tells you if this node is related to a query request or not. And we also have weight. For every node, the weight means the number of the execution times of this node appeared in the trace if we're starting from some initial trace. After we have everything ready, we will define the semantic-based adaptivity, in the form of a walk on these graphs with the largest number of query requests. And this is a graph for these two round examples, and we find such a walk from L6 to A5 to X3, which contains two query nodes, and then the adaptivity is defined to be 2. Finally, we need to statically estimate this adaptivity we just defined. We propose a program analysis tool called AdaptFun that computes an upper bound on this semantic-based adaptivity. It consists of 2 parts, the graph generation and the adaptivity estimation. The reason is that since our semantic-based adaptivity, it is based on a graph, so to estimate that, we also want to construct such a graph. And we use standard program dependency graphs, and then put some query annotations by scan the code and figure out where it is query related. Also, we are add some weight. As for the weight, it means upper bound on the numbers of times each variables they can be reached. So we use a technique called a reachability bound analysis to give the weight. Now we have the graph. Then we want to estimate the adaptivity by search such a graph walk in this graph with a maximal query length, which means we need to traverse a graph. However, there's some challenges when we do that. It is first the symbolic expressions used in the weight. For example, in the graph, it can be k. And also, the while loop will introduce some cycles in these graphs. So these two things make it hard to directly compute such a maximal walk. To solve this problem, we propose another algorithm called AdaptBD. The idea of it is to reduce this task of computing the walk with a maximal query length in the dependent graph to another task, trying to find the longest weighted path in a simplified dependency graph, which is a DAG. So we simplify this graph in 3 steps. So suppose we have a graph with many cycles. We'll first partition these graphs into its strongly connected components, SCCs. And then for every SCCs, we're trying to compute its local adaptivity. The last step, we were trying to shrink these graphs by replacing every SCCs with vertices, and its weight will be the local adaptivity. After simplifications, we have a direct acyclic graph, and then we can use the BFS to find the longest weighted path. And we'll return the length as the adaptivity upper bound. And in this case, these examples, the adaptivity we find, it is the purple path from 1 plus 4k plus 1. There are also some limitations about our tool. It is not path sensitive. So for example, we have a very simple examples that has a while loop, and depending on if the iteration is odd or even, we have different query requests. And I call it to be multiple round odd. And if you look at the semantic-based graph here, B, and it shows that the weight, it is 2 over k, so it can handle okay if it's odd or even iterations. But like the reachability bound analysis, they will give a loose bound k for every node. In this case, our tool will give a loose upper bound. We implement these tools like in OCaml and Python. And our tools will return 2 results. One is the estimated adaptivity I just introduced. Another one is upper bound on the query numbers. And there are a few examples I want to emphasize here. So we tested 2 rounds. It is precise in both the adaptivity and the query numbers. Also, this is a multiple round odd I just showed. And unfortunately, we give some loose upper bound since we are not path sensitive. Also, if you look at this like a red box, we have some star here. Star means it takes too long for us to get a result because the performance, like bottlenecks for the reachability bound analysis to calculate the weight when it sees some complicated examples that contains multiple level, nested loops. So to handle this, we also have alternative implementations for these examples that will calculate the weight quickly, but imprecise. Now, our last step is we use a heuristic to use what we get from our tools to recommend what mechanisms you want to use. So if the square root of q, the query numbers, is much greater than this a times square root of log q, we recommend data splitting. In the other direction, we recommend Gaussian mechanisms. Otherwise, we recommend threshold mechanisms. We do some evaluations to test our recommendations. And the largest regressions, some machine learning, algorithms in sklearns, and some real-world adaptive data analysis algorithms. Here in bold, it is our recommendations by our heuristics. And in red is the best performance and shows that in most cases, we give our recommendation give the best suggestion. And I will conclude our works, and we present a static analysis tools, and it can analyze the adaptivity and for adaptive data analysis programs. A few things we want to do in the future is we want to improve this path-sensitive performance. Also, we want to design a better heuristics so that it can support more mechanisms. And finally, we also integrate these things into other adaptive data analysis frameworks like GNC. Thanks for coming, and you can find the artifact and the code. Yeah, I'm here for questions.
Thank you. Any questions, anyone? So I have a question about your evaluation. So the unit in this one here, so that's seconds, or what are we counting? The numbers. What are the numbers representing?
The numbers?
Yeah, all the numbers. Are they seconds, or what is
oh,
the
yeah,
unit?
yeah.
Okay.
It is seconds.
What is the use case you have in mind where it makes a...
Oh, wait, sorry. It's not a second. It's generation errors. So it is, you mean all the numbers here?
Yeah, what are the numbers representing?
Numbers representing the actual generation errors, RMSE.
Okay, all right, okay, thank you. Okay.
Thank you for the talk. I had a question about the other evaluation where you listed the size of each of the benchmarks that you did here, lines of code. So the sense I get is that they're fairly small benchmarks, but I don't know the area very well. Would you say these are realistically sized benchmarks? Are these sort of small ones that you use for a first pass, or what's your sense?
It's a small ones we use we manually have these benchmarks to cover like multiple, like a loop, like if, and we try to have some complicated examples. So, and finally, you see some very complicated examples, and we reach some like performance issues. So then we have another like alternative implementation to handle these cases. But it's quite small. Thank you.
All right, thank you again. All right, next, Long Pham will tell us about resource bounds and Bayesian inference.
Yes. Can you can you hear me? Yes. Okay, great. All right. Okay, hello. My name is Long Pham. I'm a PhD student at Carnegie Mellon University working with Firas and Jan. Today we present our work on robust resource bounds with static analysis and Bayesian inference. We study resource analysis where the goal is to infer a worst-case bound of the cost of a program as a function of inputs. The user first applies a program, say the function quicksort with input x, and also specifies a resource metric of interest, such as execution time, memory, and energy. Taking these as inputs, automatic resource analysis returns a worst-case cost bound, such as 1 + 2 times the input size x. Resource analysis has many applications. In computer security, it can be used to detect algorithmic complexity attacks by inferring worst-case resource usage and worst-case inputs of programs. Another application is to estimate the job size for job scheduling in cloud computing, where the cloud service provider wants to avoid both under-provisioning and over-provisioning of resources. Other applications include complexity analysis in the static analysis tool Infer, which is used at Meta/Facebook, and also the worst-case execution time analysis for safety-critical embedded systems. There are two approaches to automatic resource analysis: static analysis and data-driven analysis. Static analysis analyzes a source code. It is sound, that is, any result is guaranteed to be a valid worst-case bound. But it is incomplete, that is, it cannot handle all programs. Meanwhile, data-driven analysis analyzes runtime data. It always returns some inference result, but it offers no soundness guarantee. Our contribution in this work is to integrate static analysis and data-driven analysis into a single framework called hybrid resource analysis to combine their complementary strength and mitigate their respective weaknesses. In hybrid resource analysis, the user specifies which part of the source code should be analyzed by data-driven or static analysis. For example, the user may choose to run data-driven analysis on the helper function g on the slide because it cannot be handled by static analysis. We then perform these analyses on their respective code fragments and combine the inference results into an overall cost bound. Now that we have motivated the hybrid resource analysis, I will next review the state-of-the-art resource analysis, specifically static analysis and optimization-based data-driven analysis. In static analysis, we examine the source code, construct constraints defining the worst-case behavior, and solve them. Many static analysis techniques have been developed in the literature, including those based on type systems, such as ARA by Jan Hoffman, Martin Hoffman, Stefan Jost, and their colleagues. Also recurrence relations, such as Costa by Elvira Albert and her colleagues. And finally, ranking functions, such as approve and code by Eugen Giesel and his colleagues. An advantage of static analysis is that it offers a soundness guarantee, but a disadvantage is that it is incomplete due to the understandability of resource analysis in general for a Turing-complete language. Also, rewriting a program so that it can be analyzed by static analysis requires expertise on the underlying technique, so it can be difficult for any non-expert users. Next, I will describe the optimization-based data-driven analysis, which is the dominant approach in the existing literature of data-driven analysis. Examples of prior works that use optimization include input-sensitive profiling by Kopa and his colleagues, algorithmic profiling by Zabranux and his colleagues, and Danaplex by Ishimura and his colleagues. So here's the workflow. In the first step for data collection, we prepare a collection, a set of concrete inputs, V1 up to Vn, and then execute a program F on these inputs to record the input sizes and costs, C1 up to Cn. We then aggregate these pairs of input sizes and costs into a dataset. In the second step, we optimize the cost bound, which is represented by the red line in the diagram on the right. Specifically, we minimize the distance between the red line and the black dots, which denote the observed costs in the dataset, subject to the constraint that the red line must lie above all the black dots. So this is how we use optimization to infer a cost bound from a dataset of observed costs. A disadvantage of this optimization-based technique is that it doesn't incorporate the user's domain knowledge about how large the gap should be between the black dots and the blue line in the diagram, which represents a true worst-case cost and can be strictly higher than the red line, which is the result of optimization. Also, optimization provides no quantitative measure of statistical uncertainty of inferred bounds. To improve on this optimization-based technique, in this work, we propose Bayesian data analysis, where we perform Bayesian inference instead of optimization. Here's the workflow. In the first step, we define a probabilistic model, pi, of theta and d, which defines a joint probability distribution of two random variables, theta and d. Here, theta is a latent parameter. It is something that we want to infer, so it corresponds to a cost bound in the context of resource analysis. And D is an observed data, so it is a data set of cost measurements. Next, we collect observed data, the obs, and compute the posterior distribution given by Bayes' rule. In practice, however, the exact posterior distribution is computationally intractable. So instead, we run a sampling algorithm to draw a collection of posterior samples, and we use them as an approximation of the true posterior distribution. An advantage of this Bayesian technique over the optimization-based technique is that we can incorporate the domain knowledge of the user in the form of a probabilistic model. Also, the posterior distribution returned by Bayesian inference captures statistical uncertainty of inferred bounds, unlike optimization. We propose two different techniques for Bayesian data analysis. The first one is Bayesian inference of worst-case cost, or Bayes WC for short, which is in the middle of the slide. And the second technique we propose is Bayesian inference of polynomial coefficients, or Bayes BC for short. So I will next describe them in turn. In the first one, Bayes WC, the first step is to define a probabilistic model, pi, of theta, Cmax, and C, where Cmax is a hidden worst-case cost, which is represented by the blue dots in the diagram. And C. Next, we draw posterior samples of Cmax, namely the blue dots, and then optimize the cost bound indicated by the red line, just like we did in the optimization-based technique. But this time, we have a constraint that the red line must lie above all the blue dots that we just inferred from step 2, instead of the black dots. So by performing Bayesian inference on the blue dots using the dataset of black dots, and then optimize the red line so that it lies above all the blue dots, the user can add an additional buffer between the black dots and the red line. The second technique we propose is Bayes BC, where we define a probabilistic model, pi of P and C in the first step, where P is a polynomial coefficient of a cost bound, which is represented by a blue line in the diagram, and C is the observed cost. So that corresponds to the black dots. And then we draw posterior samples of a cost bound P. So this is basically a Bayesian polynomial regression where we perform Bayesian inference to infer not only the worst case cost, but also the polynomial coefficients of a cost bound. So next, I will describe our central and second contribution, hybrid resource analysis, followed by its evaluation. To design hybrid resource analysis, we need an interface between Bayesian data analysis, which runs a sampling algorithm and draws posterior samples, and static analysis, which solves constraints to infer a sound cost bound. So a key challenge is how do we coherently combine constraints and posterior samples? if we naively perform Bayesian data-driven analysis independently of the static analysis, then the posterior samples returned by Bayesian inference may not satisfy the constraints of the static analysis. So it is important to account for the constraints of the static analysis when we perform Bayesian data-driven analysis. In this work, we design, implement, and evaluate hybrid ARA, which integrates Bayesian data-driven analysis, specifically BaseWC and BasePC, and automatic amortized resource analysis, or ARA for short, which is a type-based resource analysis technique. We achieve this integration by a novel interface between sampling algorithms and linear programming, where sampling algorithms are for Bayesian inference and linear programming is for ARA. In hybrid ARA, the user specifies which code fragment should be analyzed by which method. So hybrid ARA covers a full spectrum, ranging from fully static analysis to fully data-driven analysis. On the left end of the spectrum is ARA, where the user chooses to analyze entire source code by static analysis. On the left end of the spectrum is BaseWC and BasePC, where the user chooses to analyze entire source code by data-driven analysis. In practice, it is common that static analysis fails to analyze entire source code, but can still handle a non-trivial portion of the code. In such a case, the user can choose to perform static analysis on the part of the source code that it can handle, and data-driven analysis on the rest of the source code, such as the helper function G on the slide, which we assume cannot be analyzed by ARA. So this hybrid of the two analyses lies somewhere in the middle of the spectrum. And as we will show later in our evaluation, this hybrid performs better than static analysis alone or data-driven analysis alone. We choose to focus on ARA for the static analysis part of hybrid ARA. The key idea of ARA is that each variable is equipped with a polynomial potential function from amortized analysis of algorithms and data structures. ARA infers polynomial coefficients of these potential functions by solving linear programs. We chose ARA for the static analysis part of hybrid resource analysis for several reasons, including compositionality offered by types, automatic bound inference by LP solving, precise cost bounds by amortized analysis, soundness guarantee, and cost bound certificates in the form of type derivations. So we propose two different architectures for hybrid ARA, depending on whether we integrate ARA and BaseWC or ARA and BasePC. In the first architecture, which integrates ARA and BaseWC, a key idea is to combine the linear constraints of ARA and BaseWC. So here's the workflow. Suppose the user annotates a code fragment E, which is color highlighted on the slide on the left, with the annotation stat to indicate that we perform statistical analysis on this code fragment. So statistical is what the annotation stat stands for. In the first step of this hybrid ARA, we collect runtime data D by recording the input sizes and cost of this annotated code fragment E. And then we draw posterior samples CJ max by performing Bayesian inference. And these posterior samples CJ max correspond to the blue dots in the diagram above. And then we aggregate the linear constraints from ARA on the part of the code where we perform static analysis, and also the linear constraints from BaseWC, specifically the constraint that each red line in the diagram must lie above all the blue dots. So we combine these two sources of linear constraints into a single linear program, and then we solve it using an off-the-shelf LP solver. In the second architecture, which integrates ARA and BasePC, a key idea for designing an interface between sampling algorithms and linear programming is to run reflective Hamiltonian Monte Carlo, which is a recently developed sampling algorithm that draws samples from a probability distribution restricted to a bounded convex polytope. So here's the workflow. In the first step, we collect linear constraint C0 from ARA on the part of the code that's designated for static analysis. At the same time, we collect runtime data D by recording the input sizes and costs of this annotated code fragment E. We then run reflective HMC, which draws samples from a probability distribution restricted to a convex polytope. And this convex polytope is a feasible region of the linear constraint C0. Also, the posterior samples we draw in this step are the typing judgments that encode the polynomial coefficients of potential functions. And then in the last step, we substitute these typing judgments that we drew in step 3 into the linear constraints C0. And then we solve the resulting linear program. In the last step, we don't need to worry about the possibility of the posterior samples breaking the constraint C0, because in step 3, when we run the sampling algorithm, we draw samples from the feasible region of C0. So any sample we draw is guaranteed to already satisfy the constraint C0. Next, let me show the example evaluation of hybrid ARA using the benchmark of quicksort. Our resource metric of interest is the cost of comparisons, each of which varies between 0.5 and 1.0. Here we plot 6 posterior distributions. The first row is for data-driven analysis. The second row is for hybrid analysis of quicksort, where we perform data-driven analysis on the partition function, which is used inside quicksort, and static analysis on the rest. The first column is for opt, the second column is for base WC, and the last column is for base BC. In each plot, the red line indicates a ground truth cost bound, so that's what we aim for in resource analysis. The black dots are the observed costs in the dataset, and the solid blue line is the median cost bound in posterior distributions, and the light blue shade is the 10th to 90th percentile range of the posterior distributions of inferred bounds. If we compare these plots horizontally, then we see that Bayesian analysis is more accurate than the optimization-based technique, because the posterior distributions of the 2 Bayesian techniques are closer to the ground truth, namely the red line, than the cost bounds inferred on the first column, namely optimization. Also, if we compare the plots vertically, then we see that hybrid analysis is more accurate than data-driven analysis. For the full evaluation of hybrid ARA, we have curated 10 benchmarks, all of which cannot be handled by conventional ARA. This is a table from the paper showing the percentages of sound cost bounds from posterior distributions. If we compare the soundness proportions between Bayesian techniques, which we propose for this work, and the optimization-based technique, then one finding we can make is that base WC and base BC have higher proportions of sound bounds than opt, which is optimization. Also, if we compare hybrid analysis and data-driven analysis, then we see that hybrid base BC and base BC, hybrid base WC and base BC have higher proportions of sound bounds than the data-driven counterparts, namely data-driven base WC and base BC. So in conclusion, we have 2 takeaways. The first one is that Bayesian resource analysis, which is our first contribution, is more robust than the optimization-based technique, which is a dominant approach in the existing literature. Also, the second takeaway is that we designed hybrid resource analysis by integrating static analysis, specifically ARA and Bayesian data-driven analysis. And we have empirically shown that hybrid resource analysis is more accurate and robust than data-driven analysis. And also, it mitigates the incompleteness of static analysis. We have further details available in the paper, including type-based formulation of hybrid ARA, 2 soundness theorems of hybrid ARA, and full experiment results. Thank you.
Questions?
Hello. Yes.
Thank you for the talk. Have you measured, or can you, do you have an intuitive idea of what the overhead of annotating this is? And sort of beyond that, if there's a way to automatically pick which approach to use for which part of the code instead of having the user have to decide that?
Right. So in this work, we assume that the annotation is already given by the user, because the user may have their own domain knowledge to figure out maybe which part of the code should be analyzed by data-driven or static analysis. For example, maybe you have a part of the code that has a logarithmic cost bound, which cannot be analyzed by ARA, because ARA only supports polynomial cost bounds. So in that case, maybe it's better to ask the user to use their domain knowledge to provide the annotation. But regarding automation, it's possible to automate it because, for example, we can search the, so we can traverse the source code, and then see whether any part of the code can be analyzed statically using ARA. And then if that fails, then we can gradually expand the scope of the code that's supposed to be analyzed by data analysis. So certainly it's possible to automate it.
Thank you.
Okay, one last question. Oh, sorry, Evan. Yeah, Aditya, go ahead. I just have a very basic question. So
sure.
Are these bounds supposed to be tight? So should there be an input that actually exercises that worst case behavior?
No, the goal is not to infer a tight bound, but the goal is to infer a sound worst case bound.
So when you use this data-driven techniques, do you get soundness? Or
soundness, you said?
Like,
no.
Is it actually a worst case bound? Or?
So that's a limitation of data-driven analysis. So we don't, if we use data-driven analysis, then it's impossible to provide a soundness guarantee.
Right. Or this hybrid. So I guess I was wondering in the context of those applications, can you actually use this technique for any of those like security, WSET?
Maybe not for security. So sure. So it depends on the application domain. If the user wants 100% soundness, then hybrid analysis may not be suitable. But for example, in cloud computing, where the cloud service provider just wants an accurate estimate, which doesn't have to be sound, then I think this is a suitable application of hybrid analysis. Yeah.
Okay. Thank you. Thank you again. And the next talk is about CFL reachability and will be given by Camille.
Hello? Okay. Is that working? Yeah. Oh, yes. Okay. I'm not sure why. Oh, there it goes. Good. Okay. Hi, everyone. I'm Camille Bosu, and today I'm going to be presenting context-free language reachability via skewed tabulation, which is a joint work with my co-author, Yusheng Lei, and our advisors, Yulei Sui and Qiren Zhang. So there are two parts to this title, context-free language reachability and skewed tabulation. I'll start with a bit of an overview of our idea, and then I'll dive into some background to explain what everything means, and then our approach. So the overview of our idea is that skewed tabulation will scale context-free language reachability by skewing parse trees both statically and dynamically. And the insight for this idea is that during CFL reachability solving, skewed parse trees tend to encounter fewer wasted computations while generating summary edges. So what does all of that mean? Let's start with some background on context-free language reachability. CFL reachability is a fundamental framework for program analysis like the ones we've heard about today. And all of these analyses, as an example, can be reformulated as context-free language reachability problems. CFL reachability, or an instance of CFL reachability, has two inputs, a context-free grammar CFG, which represents the analysis specification for the program analysis, and an edge-labeled graph G, which is the abstraction of the program that you're analyzing. Let's go over an example. So here we have an input CFG and an input graph G. And let's take a look at the path from S to W, labeled by the string CDB. So this CFG is composed of non-terminals and terminal symbols, where the terminals are lowercase and represent the alphabet of strings that we can generate with this grammar. And starting from the start non-terminal, we can follow grammar rules, starting with S, and then following the rule S generates AB, and then A generates CD, and B generates B, and we obtain the string CDB. So that, following those rules in the grammar, we get the string CDB. And this means that the string CDB is in the language of this grammar. And because CDB also labels the path from S to W, we say that W is S reachable from S, where S is the start non-terminal in our grammar. Similarly, X and T are S reachable from S in this example, following the B generates BB rule. So the output of CFL reachability is the set of S reachable pairs in the input graph. Now let's talk about tabulation. So tabulation, or RHS tabulation, which stands for Reps Horowitz Sagiv, is a method to calculate and record results to avoid redundant computation in CFL reachability. So going with our same example from previously and following the path from S to W, RHS tabulation takes edges one by one and checks the adjacent edges to that edge, and then does a bottom-up approach using the input grammar. So taking the edge pair CD, for example, we check if any of the rules in the input grammar have a pair CD on the right-hand side of that rule. And there is. This rule A generates CD, and therefore to record that information so that we can use it later, we insert an edge into the input graph labeled by the non-terminal A. And we do the same thing for this edge B. And these later inserted edges are called summary edges because they summarize reachability information. So we can use that information again later on when we encounter these edges in this work list algorithm. Let's say we encounter the edge from S to V labeled by A, and we notice this neighboring edge from V to W labeled by B. Following the same procedure, we see that there's a rule S generates AB, where AB is on the right-hand side. And so we've discovered a new summary edge S. And this S edge from S to W summarizes the reachability information that we found earlier, which is that W is S reachable from little s. So this process is sort of similar to the parse tree that we generated earlier, and we can represent this in the same way. But the difference is that this is a bottom-up process. So instead of going from S and generating AB and then CD and B, we started from CDB, and then we went backwards to see if there was an S path from S to W. And we can see a parse tree structure for the path from S to T as well. And this is just slightly more complex, and we'll go into this example more later. We also define this idea of summary degree. So along a graph path, for example, from S to T, we define the summary degree as the number of summary edges along one graph path that were generated by the string of that particular path. And this doesn't look too intimidating with this particular parse tree, but this is actually not representative of the summary edge for this path because tabulation is a bottom-up procedure. So actually, the set of parse trees for all summary edges along a path from S to T form a forest, which is a set of trees, and shows the summary degree of that path more accurately. So this looks a little bit scarier. Here is the summary, or the parse forest for this graph path. And the interesting thing here is that there are certain summary edges in this parse forest, namely this one, that are actually not used to compute any information that we actually care about at the end. So if you recall, the output of this algorithm is the set of S edges, and here this B edge is not used anywhere in the computation of those S edges. So this brings us to our approach, which is the skewed part of this title. And the motivation is exactly what we just noticed. And we'll also notice the following, which is that we can actually come up with an equivalent grammar to the original one here. And represented under is the corresponding parse forest for the exact same graph path and the same grammar, but it looks a lot less crowded. And we call this parse tree more skewed just because of its structure. But actually what we mean is more skewed means a smaller summary degree. So our motivation is that skewing parse trees can reduce the amount of computation when generating edges for CFL reachability. So there are a couple of challenges. Firstly, we don't want to affect correctness, so the most important thing, of course, is making sure that the set of S edges is not affected by anything that we do. But also we want to make sure that the modifications we make are not going to reduce the summary degree in some cases, but make it worse in others. So we need a guarantee that the modifications we make are not going to affect any graph paths worse. There are two parts to this approach. There's a static part and a dynamic part. And the static part amounts to a grammar transformation in a pre-processing stage. So the main idea is to identify recursive behavior, like the one in this B symbol, and propagate that up the grammar to S non-terminals. So take the recursive behavior of non-S non-terminals and promote them to the start symbol. So let's go over some grammar rule terminologies to explain the rest. Firstly, recursive grammar rules are of this form where the non-terminal occurs both on the left and right-hand side. Transitive rules are special recursive rules in which it's all one non-terminal. And linear rules contain at least one terminal symbol on the right-hand side. So now I'll define this idea of a cyclic non-terminal. A cyclic non-terminal can be left cyclic or right cyclic up to some epsilon handling, and this means that they only have left or right recursive rules. Or doubly cyclic, in which X has one transitive rule and all other associated rules are non-recursive. And we identify these rules in the input grammar, for example here, and what we want to do is use that rule and instead end up with a parse tree that looks a little bit more like that, where the recursive behavior has been propagated up to the S non-terminals. And the idea here is that we needed to compute the S non-terminals anyway. So we're not actually adding any computation. We're just delaying something until later, and we had to compute those edges anyway, so we're getting rid of an intermediary that we didn't need. So sort of as I just alluded to, this resulting grammar on the right doesn't contain the B non-terminal, but that's fine, because the B non-terminal was not part of the output anyway. So here, for a more concrete example, we identify a right cyclic non-terminal, and we can propagate that cyclic behavior in the form of recursion up to anywhere that this N non-terminal is used. So in this case, it's an S non-terminal. We propagate that up, and then we have some epsilon handling because we don't need that rule from earlier anymore since N has an epsilon rule. And now that N is completely recursive, we can propagate this recursive behavior up to the S rule at the top. So this is our static approach. But there's another part of this approach as well. The static approach can't do everything, and this is our dynamic part. So for the dynamic approach, we also say that we skew these parse trees during the online process by modifying the CFL reachability solving. So traditional tabulation adds all newly generated summary edges into the graph. But we identify a special type of edge that we're calling propagating edges that are only used to propagate reachability information, which means that they don't actually need to be inserted into the graph. So there are two types of propagating edges. Static propagating edges, which are labeled by propagating non-terminals, which we will define in a minute, and dynamic propagating edges, which are generated in a particular way. So these depend on how they appear in the work list. So in this case, they are generated by transitive rules in which all other binary productions containing this non-terminal are recursive. So first of all, for the set of propagating non-terminals, we call a non-terminal propagating if it's only used in linear rules. So in this case, recall linear rules are rules that have a terminal on the right-hand side. So we've identified CAI as a propagating non-terminal. And all we do is annotate the grammar and make note of this statically. So remember, we also have dynamic propagating edges. And so now we'll get into how we treat those two types of propagating edges at runtime. So the dynamic skewing algorithm is very similar to the standard algorithm. One difference, we initialize a set of propagating edges to handle those edges that we won't insert into the graph. And then we initialize this with an empty set. And the algorithm itself has a work list as usual, and a skewed grammar, and the regular edge set. And this actual loop part is exactly the same as the standard algorithm, We go through the work list and check the incoming and outgoing edges, but the difference lies in this update function. So instead of updating the regular edge set when we encounter a propagating edge, we update our separate propagating edge set. And we add any propagating edges to that set and to the work list if they're not already there. And the standard edge treatment has not changed in this case. This algorithm is compatible with other improved CFL reachability solvers. It doesn't affect anything. For example, POCR has a special treatment of transitive rules to improve efficiency in handling these rules, and these two approaches don't conflict and are orthogonal. So in terms of formal guarantees, first of all, of course, we have correctness. We guarantee that the skewed algorithm has the same set of S-reachable pairs, but also we have this at least as good as guarantee, which I alluded to earlier. The summary degree along any graph path for any input graph is at least as good as that of the baseline with the original grammar, if not better. And the proofs of these can be found in the paper. So now moving on to the evaluation. We evaluate on 3 client analyses, the classic alias and value flow analyses, as well as a polymorphic taint analysis, which is to show the generality of our approach. And our benchmarks are Spec CPU 2017. This is a table from the paper sort of explaining the statistics of the different graphs that we run on. So let's get into first the results of the static skewing. I've highlighted in green the start non-terminals since they're not all called S in our input grammars. And we can see that for the cases of alias and taint analysis, indeed some recursion has propagated up to those start non-terminals. Yes, but for value flow, nothing has changed in terms of the static skewing propagation. However, in all 3 of the cases, the propagating non-terminals were populated, so those can be used dynamically. Our evaluation compares 3 approaches, CFL skewed, which is our approach, CFL RHS, which is the traditional algorithm that I presented earlier, and Soufflé 8, which is a state-of-the-art data log tool that can also be used for CFL reachability, and this is an 8-threaded version, and we use this to show that our single-threaded approach is comparable to an 8-threaded multi-threaded approach for the same problem. So first, let's get into the reduction of non-S summary edges. So this might look a little bit surprising, but remember that we can only reduce non-S summary edges, and so we're not measuring those in this graph. But here we can see that we've reduced a lot of the non-S summary edges, especially in the case of alias analysis. That's partly because of the propagating non-terminals, which are not inserted into the graph, but also because of the modifications in the grammar, which made certain intermediate edges that were not necessary to the language disappear. And for taint analysis, the results are the least impressive, but still we're getting up to 50% reduction in non-S summary edges in some cases, which is pretty good. Then in terms of speed, we have the 3 analyses here. Our results are in green, and these are normalized to the standard evaluation, which is normalized to 1. So here the numbers that you're seeing are times for speed up. So the maximum, I think, here is for alias analysis, so that's a 6 times speed up. But we can see in most cases for alias analysis and taint analysis, we are doing a lot better in or we're always speeding up by a significant margin. You may notice that for taint analysis, there are some results that are missing. That's because this is a more intense analysis, and we had like a 24-hour timeout, and some of these results didn't finish. However, in all cases that it did complete, our analysis was able, or in all cases that some of the analysis did not complete, it's never the case that either RHS or Soufflé completed, but we did not. And then also for value flow analysis, the speed up is slightly less impressive. However, we're still doing marginally better in all of the cases. Now for memory usage, here we can see sort of the price of a multi-threaded application for some of the Soufflé cases. Lower is better in this case, so these are like percentage of memory compared to the baseline that we're using. And again, in all cases, we're using less memory. This makes sense. We have less summary edges to keep track of, and so the amount of things that we're tracking at runtime is reduced. So in conclusion, our key idea was that we can have tabulation that produces a lower summary degree over all graph paths by focusing and analyzing the input grammar CFG. And our approach has two parts to handle this, a static grammar transformation and also a dynamic treatment of special edges that we name propagating edges. And though some grammars may appear more skewed than others in certain cases, the particularity of our approach is that it guarantees a better summary degree over all graph paths in terms of the initial input grammar. And in practice, we can see that this approach dramatically improves both the speed and memory usage of CFL reachability over the standard algorithm. Our artifact is available on Zenodo, and you can reproduce our results with the benchmarks that are in our experiment. And that's the talk.
One quick question.
So these grammar transformations, are they confluent? And if not, is there sort of an optimal order in transforming the grammar or do you search for the one that produces the smallest scheme, or what do you do?
So basically, we look at things in terms of, I guess I simplified some of the explanation for the talk, but we look for, we accept a set of target non-terminals, which we don't modify. So usually you include the start non-terminal in that. And then we look at all non-terminals that are cyclic and that are used in recursive rules. And there isn't an enforced ordering, like we don't do a search on doing different optimization passes. We just sort of do the first thing. I guess.
So it's a greedy.
It's a greedy approach. Yeah, the problem, as I'm sure you know, with grammar transformations and grammar things in general, is that most of checking if things are equal is generally undecidable. So, yeah, we have to be sort of greedy in the things that we transform. Yeah.
Okay. All right, if there are more questions, take them after the session. Thanks again.
Thank you.
Right, for the last talk, it's about analysis for regular expressions. I will begin by Konstantinos.
All right, hi everyone. I'm Konstantinos Mamouras, and I will talk about static analysis for checking the disambiguation robustness of regular expressions. And this is joint work with Alexi Leglonek, Angela Lee, and Agnisham Chattopadhyay. So I guess most of us already know that regular expressions, or regexes, have several applications on text analysis. Some of the tasks that we can solve with them is checking whether a string has a certain form, or checking whether a string contains a pattern, or to find the occurrences of a pattern inside a piece of text. The first two problems are essentially the classical membership problem, but in this talk I will be focusing on the third task, which I call match extraction. For our results, we will use a very classical syntax of regular expressions, where they're built using concatenation, non-deterministic choice, and Kleene star. And I will also use a little bit of syntactic sugar for Kleene plus and the optional operator. So here is an example of a task. Let's say we want to extract substrings that have the form of a floating point number. Here is a regular expression that can be used for this task. I will explain it very briefly. So this is a character class that matches a single decimal digit. The sub-expression describes the optional sign symbol. Now this sub-expression specifies the integer part of the number. And finally, this sub-expression describes the optional fractional part of the number. So here is a piece of text from which we would like to extract the substring 28.3168. But notice that the substring 8.3 is also a match for the pattern. And so is the substring 168. In fact, there are many more substrings that are matches for the pattern, but we care for none of them. So how do we specify the desired match out of the many possible ones? One answer to this question is given by the so-called POSIX disambiguation policy that says choose the longest out of the leftmost matches. And then another answer is the greedy or PCRE disambiguation policy that again says choose a leftmost match, but then further disambiguate by using the following two rules. If we have a Kleene iteration R star, then we want to repeat R as many times as possible. And if we have a non-deterministic choice, then we prefer the left choice over the right choice. The majority of regular expression engines out there either use POSIX disambiguation or greedy disambiguation. And this raises the natural question of whether we can safely reuse patterns across these two classes of regular expression engines. This notion of safe reuse is formalized as follows. We will say that a regular expression is disambiguation robust, or just robust for brevity, if for every input string, the match that is preferred according to the POSIX policy is exactly the same as the match that is preferred according to the greedy policy. Okay, here is the pattern that I showed in the previous slides, and here is another pattern. At the top level, it's a non-deterministic choice, and the left choice specifies a number that is just an integer. The right choice specifies a number that has a fractional part. So you probably can observe that in terms of classical language theoretic semantics, both these two regular expressions recognize exactly the same set of strings. However, the first one is robust, but the second one is not. In fact, the string 3.14 witnesses this non-robustness because the POSIX policy would match the entire string, but the greedy policy would only match the prefix of the digit 3. So to see whether non-robustness is an issue in real applications of regular expressions, we have considered 4 datasets that in total contain 10,000 regular expressions. Here are the main observations that we made. About 4% of the regular expressions in these datasets are non-robust. Additionally, we saw that real input strings witness this non-robustness. This means that non-robustness is not just a theoretical problem, it is indeed an issue that arises in real applications of regular expressions. As an example, let's take a look at this pattern that specifies an IP address that I took from the Snort dataset. And here is a string that I extracted from a real network traffic trace file. This string indeed witnesses non-robustness for the pattern that I'm showing. So our notion of robustness naturally gives rise to a decision problem, which I call is robust. If we're given a regular expression R as input, is our disambiguation robust? And our first theorem is a hardware result that says that the problem is robust is p-space hard, which is something that we prove with a reduction from the universality problem for regular expressions. For the rest of the talk, I will try to give you a little bit of high-level intuition as to how we can actually solve the is robust problem. To obtain our results, we will use a model that I call greedy non-deterministic finite automata, or GNFAs. And this is a variant of the classical epsilon NFAs that we know. But every non-final state has one out of 3 types. It can either be a guarded state, which means that it has exactly one outgoing transition labeled with a character class, or it can be a jump state, which means that it has exactly one outgoing epsilon transition, or it can be a choice state, that has exactly two outgoing epsilon transitions, one of which is labeled with epsilon/0, and the other one is labeled with epsilon/1. So the intuition here is that the transition that is labeled with epsilon/0 is preferred over the one that is labeled with epsilon/1. And these choice states are used to implement the greedy semantics. A key concept here is the concept of a disambiguation trace, or just trace, which is a string over zeros and ones. And a trace gives us the sequence of choices that are made in a path. Now, for the greedy semantics, the idea is that we want to choose a path that has a lexicographically least trace. And at this point, I should acknowledge that prior work has already considered such automata in the context of full regular expression parsing. To describe GNFA execution, both for the greedy and for the POSIX semantics, I will need three notions: token, priority, and configuration. For greedy execution, a greedy token is a triple Q, I, tau, where Q is a control state of the automaton, I is a start position in the string, and tau is the disambiguation trace of the corresponding execution path. The greedy configuration now is a linearly ordered list of the greedy tokens. For the POSIX execution, on the other hand, a POSIX token is a pair Q, I. A priority is simply a start position I, and a POSIX configuration is a partially ordered list of POSIX tokens. Both for greedy and for POSIX execution, at every step of the computation, we consume a letter and we update the configuration. And here's where priorities come into play. At every step, we process the tokens of a configuration in order of priority. So given all these things that I just mentioned, how can we actually check the robustness of a regular expression? So here's a first thought. Let's consider the greedy and POSIX executions over every possible input string, and we should check that there is always agreement in output. But of course, this involves an infinity of checks. We have to work a little bit harder to obtain an actual algorithm. Our first observation is that when we scan a string from left to right, disagreement between greedy and POSIX can only occur by having a new, better POSIX match, while the greedy execution does not report a new match. And the second crucial observation is that we do not even need to record the greedy and POSIX priorities in order to identify non-robustness. This means that we can drop all this information that has to do with start positions and disambiguation traces. So this gives rise to the concept of a stripped greedy execution, where a configuration is an element of list of Q, which means that it is a collection of linearly ordered control states. And correspondingly, we have the stripped POSIX execution, where a configuration is an element of list of set of Q. So we think of it as a collection of partially ordered control states. Now, the robustness analysis checks that the stripped greedy and POSIX executions are always in lockstep. This means that they always agree in terms of finding new best matches. This analysis can be formulated as the exploration of a finite graph that I call the robustness graph. It consists of vertices that are triples, where the first component is a stripped greedy configuration, the second component is a stripped POSIX configuration, and the third component is a Boolean value that indicates whether a match has been found so far or not. So let me use the example of the GNFA for the regular pattern A star AB option in order to illustrate the exploration of the robustness graph. And in particular, I will be using breadth-first search because I would like to find a witness of non-robustness that is of minimal length, if one exists. So in the beginning, we construct the initial vertex. And notice here the annotation on the edge. This annotation says that greedy and POSIX agree because both of them report on a match at the very beginning. This is because the regular pattern accepts the empty string. Then we continue our exploration by considering the edge on the letter A from the initial vertex. This gives us vertex 1 of the graph. Again, we see that greedy and POSIX are in agreement because both of them report a new best match. Then we will explore the edge on the letter B from the initial vertex. Again, greedy and POSIX agree because both of them do not report a new match. And also notice that in vertex 2, both configurations become empty. Now we will continue our exploration from vertex 1. If we consider the edge on the letter A, then we form a self-loop on the vertex. And we see that greedy and POSIX again agree. Both of them report a new best match. And then let's consider the edge on the letter B from vertex 1. And here finally we notice that greedy does not report a new best match, but POSIX does, which means that we have just identified non-robustness, and we can read off the witness of non-robustness by following the path from the beginning until this point where we witness the non-robustness. And in our case, it's the string AB. By the way, here the analysis would stop, but this is not the complete robustness graph. Here is the part that is missing. Okay, using all these ideas that I just described, we can now finally prove that the problem is robust, is p-space complete. I have already discussed that the problem is p-space hard. It remains to see that the problem belongs in the class p-space. So the first observation is that the robustness graph has exponential size, but we can construct it on the fly. And we can explore it using a non-deterministic polynomial space algorithm that intuitively, at every step, guesses and checks the witness of non-robustness letter by letter. Then finally, we invoke Savage's theorem, and we obtain the desired result. We have implemented the robustness analysis algorithm that I just described, and I call this the base algorithm. We have also implemented some performance optimizations that rely on some easier to check sufficient conditions for robustness before we run the base algorithm. I'm not going to be able to give you the details of that. More information about these optimizations can be found in the paper. In these plots, you can see the comparison between base and opt. The horizontal axis shows the running time of the base algorithm in milliseconds, and the vertical axis shows the running time of the optimized algorithm. Every point in these plots corresponds to a regular expression, and the observation is that all points, or rather most of the points, are substantially well below the diagonal, which means that the optimized algorithm is faster than the base algorithm. Here is a table that summarizes the results. The base algorithm needs a little bit over an hour to analyze all the regular expressions in our data sets, and the optimized algorithm needs roughly 2.5 minutes to do so. Another thing that I should mention here is that the base algorithm fails to analyze roughly 3% of the regular expressions because the space blows up. But the optimized algorithm fails to analyze less than 0.04 of the regular expressions. I'd like to conclude with a summary of the main points of my talk. First of all, we have defined the novel notion of disambiguation robustness for regular expressions, and we have seen that non-robustness is an issue for reuse in practice. We have shown that the problem of deciding robustness is p-space complete, and we have proposed an algorithm for robustness analysis that relies on the exploration of an exponentially large robustness graph. Finally, we have implemented our robustness analysis algorithm, and we have shown that it can analyze the vast majority of regular expressions in the data sets that we have considered in a few milliseconds per regex. This concludes my talk. Thank you for your attention.
Fitz. Thank you very much. Wonderful conclusion to the conference. But I've worked on some of those things myself, so I was wondering, it seems like you have developed a sort of monotonic way of representing the states of, for a streaming exploration of an input, you could say, by representing the not only the greedy state, which looks very recognizable to me, but also the longest prefix one. So, is that a basis then for having a sort of single pass streaming longest POSIX style algorithm that can do full parsing or of regular expressions? Here you're actually studying the relation of those two.
Right. That's a great question. So actually the semantics that we consider will only look at the match for the entire regular expression. So we will not further parse the substring in order to go into the realm of full parsing. We will just identify from where until where the overall match is. So I would say in that case, it would be a lot easier to get a streaming algorithm. But in the case of full POSIX parsing, I don't think it would be such a simple step to go from what we have developed in the paper to an algorithm that can give you the full parse tree for POSIX semantics. I think that might require some additional algorithmic tricks.
I'd like to chat with you after that.
Yeah, I'd love that.
Okay, I have one question. So I wonder if there are some connections between this robustness problem and grammar ambiguity. So there are some techniques that analyze ambiguity of arbitrary context-free grammars. So have you thought of that connection?
Right, so it's a different notion. So the notion of ambiguity also exists for regular expressions as well. But it's an easy problem. Like to check ambiguity for regular expressions is just a simple reachability algorithm over a small automaton. So this notion is fundamentally different.
Right, but I wonder if you could encode this robustness problem as a grammar ambiguity problem, or maybe that doesn't make sense.
I don't see the encoding right now, but maybe there is a connection. Yeah.
Hey, I was wondering, so these tools, they don't just differ in how they match the longest string. Oftentimes they differ in the actual regular expression language. So like they have more things than these things, for example, matching things after, like a kind of look ahead sort of things. Have you looked at, could this be adapted to support kind of more kind of in the wild regular expressions?
That's a great question. So before I get to look aheads, I want to say something about another feature that takes us beyond classical regular expression back references. Our results actually also show that deciding robustness for regexes with back references is undecidable. So we can forget about regular expressions with back references. Now for look around, I believe that this can be accommodated. I don't think that the essence of that extension would be fundamentally different than what I showed. I feel like it would become a little bit more hairy to describe, but I think fundamentally the same idea as what I showed today should work for pure look around. So both look behind and look ahead, actually.
Okay, so that concludes the session and the conference. So thanks again for all the great talks and great questions.